All right, in this enterprise managed VPN lesson, which is really the second lesson of this module, we want to talk about enterprise managed VPNs. And what do I mean by enterprise managed VPNs? We're talking about VPNs that the customer establishes, that the customer sets up, doesn't use a third party. Most cases, we're talking about what? We're talking about GRE. But there are other options, right? IPSec with VTI, GETVPN, DMVPN. We're going to talk all about DMVPN in this chapter, Phase 1, Phase 2, and Phase 3. We'll talk about MPLS VPN over a GRE DMVPN. We'll talk about DMVPN redundancy, and then we'll get into SSL VPNs. And then finally in this module, excuse me, I'll switch the slide here. Finally in this module, we're going to be talking about FlexVPN architectures, right? And what a FlexVPN is. So a lot of different VPN options, but all of these are enterprise managed VPN options. The WAN itself allows us to connect our sites, but we know that we don't necessarily have to run a VPN technology over that WAN, at least not a service provider provided VPN technology. So there are many, many different ways to connect our remote sites. And we mentioned some of those ways the last time. You can build your own infrastructure. You can lease a VPN solution from the provider, which is what we talked about in the entire last lesson there. Or we can configure our own VPN solution over the internet. We'll talk about the pros and the cons of each one of these options, but in this lesson, we're primarily focused on those enterprise managed VPN solutions. Some of this stuff you guys have probably already had some experience with and worked with in the past, namely DMVPN, possibly GETVPN, but we'll talk about you know, the differences and how each of these VPN solutions provide features or options for the client connecting their remote locations. A virtual private network is really just a term that's used to describe the connection of remote branches and users over some sort of third-party link, typically. All right, and that's usually when we think of a VPN concept, that's what we think about. But it's not always the case, right? Enterprises can actually use their own equipment and implement their own VPN solution. The goal of the VPN connections is to allow us to connect our remote branches and users to a central site, which will allow users to access corporate resources at the central site, but do that in some sort of secure and efficient manner, right? VPN connections are established over some sort of third-party infrastructure, like the internet or some sort of provider-managed VPN, and there are pros and cons to implementing either option, right? If the only goal, which usually is the primary function of a VPN, is to extend private networks over a public network, then we can use the internet as our underlying network for those VPN solutions, and the VPN connections can be established over this insecure infrastructure with the use of encryption, and we know that encryption would be required, right, since sending the data in clear text exposes that data to confidentiality breaches and integrity breaches and so on. Why would anybody ever consider using the internet as opposed to a provider-managed VPN solution? Well, the main reason would be cost, right? It's much cheaper, or relatively cheap in comparison, using the internet for our VPN solution as opposed to a provider-managed VPN service. The primary drawback of using the internet as your underlying technology, though, is that you don't get QoS support. There's no way to support quality of service over the internet using this enterprise managed VPN solution. all the traffic that's being routed over the internet is going to be routed with best effort. There's not going to be any service level agreement or guaranteed minimum service levels for that. So to overcome that particular drawback, we use provider managed VPN services as our underlying network to implement a VPN solution over that particular network, right? So we would combine kind of two of those aspects. The motivation or the reason why customers implement enterprise managed VPNs over a provider managed VPN solution is that we have that SLA in place for the connectivity, and we have that guaranteed service for connectivity, and we want to implement our own routing infrastructure without provider involvement, right? So what would be, in the case of creating a managed VPN solution with an enterprise VPN solution, what would be a common deployment model? Typically some sort of layer 2 MPLS VPN, VPWS would be one, and then adding on top of that layer 2 VPLS or VPWS solution, some sort of enterprise managed VPN solution. It's good practice to establish some sort of traffic encryption, even if you're using a provider managed VPN service, because VPN doesn't necessarily mean encryption. It doesn't mean anti-replay protection. It doesn't mean integrity protection, because it's not really, I mean, when a lot of people hear the term VPN, they tend to think of those things, but MPLS doesn't provide that functionality. Frame relay doesn't provide that functionality. ATM does not provide that functionality. So the onus or the reason for running this enterprise managed VPN over a provider managed VPN is to gain that functionality over that VPN. The drawback, of course, is that you have to pay for it, right? It's a lot more expensive to have some sort of managed VPN solution than to run your own completely autonomous enterprise VPN solution over the internet. All right? There are two main categories of VPN solutions that exist: site-to-site VPNs and remote access VPN solutions. We know what the goal generally is of a site-to-site VPN solution. It's to connect two networks together over some sort of insecure transport. That could be GRE with IPSec, DMVPN, GETVPN, and IPSec VPN. And all those are kind of examples of that. They provide virtual tunnels to forward traffic from the branch location to the corporate location, and then also add in the security functions and the features that we would expect to provide for the CIA triad: confidentiality, integrity, and availability. A remote VPN solution is really just to connect remote users to a central site. This could be SSL VPN, IPSec VPN in the past has been used as a remote VPN solution as well. Primarily, it's going to be some sort of client-based or clientless-based SSL VPN today. The clients have special software on their computer, or they can use a web browser and not install a client. But there's some limitations to that as well. All right, particularly when it comes to running native applications on the operating system, we generally would like to see a client-based VPN solution for that, as opposed to a clientless VPN solution. So we are going to go down this road. We're going to talk about all these different types of VPN, enterprise VPN solutions, talk about the benefits and the plus sides and the negative sides to each solution, so that you guys can get a better understanding of what these solutions are and how they provide enterprise class VPN services for your network. The first one we'll talk about is what we call generic route encapsulation. If you've ever worked with GRE in the past, you know that there are some serious limitations to GRE because it's really just a tunneling protocol. It's not necessarily a traditional VPN protocol. It's considered in the VPN class because it does create a virtual link or a virtual tunnel, but it doesn't provide for security features, all right? But in order for us to establish any kind of enterprise managed VPN, we have to have a solution that will allow us to tunnel any packets, multicast packets, broadcast packets, unicast packets over whatever the transport network is. The GRE can tunnel unicast packets, it can tunnel multicast or broadcast packets. So this is a great tool and a great application to allow us to route or tunnel routing protocols, tunnel regular routed protocols and IP unicast and multicast and broadcast traffic. All right. GRE is a protocol that provides a tunneling feature. It doesn't provide encryption. It creates a virtual point-to-point connection between two routers. And the routers themselves encapsulate traffic with something called the GRE header and a new IP header. This new packet gets forwarded to the router on the other end of the tunnel using the external IP header to make those forwarding decisions. So just like in IPSec VPN tunnel mode, we create a new header that allows us on the outside of the tunnel header that allows us to actually make forwarding decisions. Once the data is received at the other side, the router on the other side of the tunnel strips off that outer IP header and the GRE header and then forwards the packet based on the routing table and the internal IP packet header. GRE was originally developed by Cisco, but it is now an IETF standard. All right. So it's supported on many, many routing platforms. It is an IP protocol. All right. It is an IP protocol. It runs over, well, it's IP protocol number 47, I believe. Yeah. IP protocol 47. Okay. Excuse me, had to stretch there for a second. The main advantage of using a GRE tunnel is that it can actually transport protocols that normally wouldn't be passed over the network, right? And that's a great, because we're talking about the internet, right? Ultimately, that's what we're talking about. Well, we know that multicast traffic doesn't get routed over the internet. But if we establish a GRE tunnel, we'll be able to pass that traffic between two sites, even if it's multicast traffic. The downside to GRE is it doesn't provide any cryptographic traffic protection. All right, so typically we'll pair GRE with IPSec. And the IPSec, the IP security component, will provide that traffic protection. All right. The other disadvantage of GRE, and you guys may have run into this in the past, is that GRE does not define any kind of keep alive mechanism. Cisco has something that they've integrated into GRE that provides keep alives, but it's a proprietary function. So in the IETF standard, there is no keep alive mechanism built into the GRE protocol. Also, and this is a big consideration as well, when you implement GRE tunnels, you can have MTU issues or IP fragmentation issues, right? Why is that?
Because of the overhead of the packets?
Because of the overhead of the GRE header, right? A GRE header adds, a GRE header adds 24 bytes of overhead, right? 4 bytes itself for the GRE header, plus 20 bytes for the new IP header that was created to do the routing for the routing decisions over the internet. So we have to have an MTU value to support those extra headers that are being added on to that. And then on top of that, if you add IPSec, you're going to have even more overhead for the IPSec information, right? We'll see that later on. The biggest claim to fame for GRE, though, is that it supports multicast. And because it supports multicast, we can use routing protocols over GRE tunnels. Two endpoints of a GRE tunnel would act basically like they're directly connected to each other. So we can implement routing pretty much the same way that we would if we had a physical wire going between two devices. We can use any IGP routing protocol that we want. All right. You have to be a bit careful, right? Because you can create recursive routing loops. That would happen, of course, if you misconfigured a router in a way that it would try to route to the tunnel destination address using the tunnel interface itself. We'll talk maybe a little bit more about that later on. And then we know that recursive routing loops can cause instability, route flapping can occur in the network, and so on. So we have to make sure we have proper filtering, or we use some sort of different routing protocol for the GRE tunnels and the transport network. The transport network is usually the internet, right? So in the case of the transport network, we're usually using default routes, static routes. And then we're using a different IGP protocol that's being tunneled over GRE. So it's not something that we have to concern ourselves with a whole lot, but it is something to consider. All right. In addition, and we can see that depicted on the diagram here, GRE is usually implemented using a hub and spoke topology. The hub router has to establish point-to-point tunnels with spoke routers. So you have to have a unique subnet on the point-to-point connections between each site. If you're trying to design a highly available GRE solution, you usually have two routers at the central site and one router at the branch site. And then each hub router at the central site would have its own connectivity to the WAN network. The branch routers then connect to the WAN network with two upstream connections, and then we would implement GRE tunnels at the branch office, or multiple GRE tunnels at the branch office for high availability. Each tunnel would be connected to one hub router at the central site, and then we tune our routing protocols to select whichever primary GRE tunnel at the central site we wanted to use. Does that make sense? All right.
So you're referring to the dual clouds, right?
Yeah, essentially, yeah. At least dual tunnels, right? And maybe even separate internet connections as well, you know, or separate cloud connections. If we're running this over an enterprise, a service provider VPN solution.
Hey, Scott, I have a question.
Yes, sir.
So right now we're running a dual hub DMVPN for AWS, and then we'll be doing that for Azure. Is it possible to, and each environment or each spoke has a single router for the GRE termination point. Is it possible, and how complex would it be to add additional like backup routers at each spoke? Is that possible in this kind of a scenario?
It's completely possible because essentially you're just overlaying another DMVPN network on top of that, right? And you would use an IGP locally at the spoke site to route, you know, to whatever spoke you want to route to get back to the hub. So
okay, so it would be an so the trick would be an entirely different DMVPN network overlaid on the existing one.
Well, just parallel, right? And then
Right.
and then you would use a local IGP or maybe static routes or floating static routes or whatever to decide which DMVPN that you would actually communicate over. Does that make sense?
Yeah, part of what we're using was like weighted static routes.
Right, exactly. Floated, yeah, you're changing what, administrative distance of the static route?
But yeah, by like adding a 2, I think, I can't remember the config, like adding like whatever default route to tunnel 1 or tunnel 2 has a 2.
Yeah, that's the administrative distance. So you'd be modifying the administrative distance of the static route. The lower the number, the more preferred the static route because it has a lower administrative distance value.
Right. And then we can figure out how that works with AWS because the routing in AWS is kind of funny.
Because of what? I didn't hear the last part.
I said then we need to figure out how to work with the routing in AWS because they don't have any kind of true redundancy in AWS for routing, and you can only use static routing in AWS or Azure.
Right. And you just have to match it up, right?
What's that?
You would just have to match it up using similar functions with static routes and administrative distance values. Or you can use
the trick would be though with the route tables in AWS would be pointing to your active router. So since you have 2 routers in the environment or the spoke, the route table in AWS can only statically point to one of those routers.
Can you tie in AWS or Azure any kind of IPSLA or object tracking or anything like that?
No, the way it would have to be we'd probably have to use BSD at the environment or the spoke routers. And when it notices that the BSD peer goes down, it would have to send some kind of an API call to AWS to manually change the static route to point to it as the active router.
Yeah. That's probably the way you'd have to do it because you don't have all those integrated functions that you normally would have with like a real router.
Right, that's correct.
Hey, Aaron, there's something in Azure that has come up. It's in a preview right now. It's work around the layer 2 issues with Azure. And I'll forward that to you. We were at Microsoft the other day, and they announced that they have work around the layer 2 issues. So you're mentioning, you have to point the route to the active router, but they have come up with something, a work around that.
Okay. We can talk about offline when I'm down there tomorrow or the next day.
Of course, yeah.
Thanks.
All right. Now, classic GRE tunnels, they're point-to-point. And, we talk about MGRE and the capability of doing a multi-point GRE, and that comes down a little bit later in our discussion. But our classic GRE tunnels are point-to-point. Obviously, there's a huge limitation and scalability issue when we're implementing robust point-to-point topologies. So the introduction of multi-point GRE adds multi-point support to this classic point-to-point technology. MGRE extends the ability to support multiple GRE endpoints by adding this multi-point function, and you create something called a multi-point GRE interface. But it's not just a matter of providing the ability to have a multi-point interface to allow us to connect to several spoke sites. It actually allows us to simplify the configuration as well. Because in a point-to-point, in a classic GRE point-to-point configuration, you're having to create several GRE interfaces for each location that you want to connect to. With multi-point GRE, you only have one tunnel interface for all of the multi-point GRE peers, all right? And then those GRE tunnels use the same subnet even. And it's going to support multicast, and it's going to support broadcast and unicast traffic, just like your classic GRE tunnel. When you're using point-to-point GRE tunnels, you have to manually specify the tunnel source and the tunnel destination for each of those GRE tunnels. You don't have to do that with multipoint GRE because the learning of the peers is done dynamically. All you need to do is run a protocol that maps the tunnel IP addresses to whatever the physical IP address is on the remote side. In multipoint GRE, that protocol is called NHRP, the Next Hop Resolution Protocol. All right? Now, what NHRP does is, well, it's very similar to ARP, right? If you've ever dealt with ARP and Ethernet, you know that the Address Resolution Protocol on Ethernet allows us to discover the MAC address, the destination MAC address of a frame when we already know the destination IP address, whether that destination MAC is the MAC address of your gateway or whether it's a local host that you're communicating with. The NHRP protocol does the same thing, although we're not dealing with MAC addresses necessarily. It's going to dynamically register the mappings of the tunnel interfaces, which are virtual, and the physical interfaces of the other peers. All right? Now, what does this provide for us? Well, it provides us the ability to do dynamic registration, and it also allows the use of dynamically assigned addresses at the spoke side, which means that we don't have to have these static configurations in our GRE configuration. All right? So let's take a look at kind of a comparison of the two and look at the difference between doing your classic point-to-point GRE configuration versus your multi-point GRE configuration. In a point-to-point GRE configuration, which, by the way, we typically use for very simple point-to-point tunnels, and the goal here is to emulate basic point-to-point WAN links. Even if it's a hub-and-spoke VPN, it still would be point-to-point WAN links. So on each device, there's a separate GRE tunnel interface that gets configured and mapped over to a GRE peer. Each of those tunnels require a unique IP subnet. We don't have to use NHRP because both the tunnel destination and the tunnel source are statically configured, and it's going to support all of our different traffic types: unicast, broadcast, and multicast. In a multipoint GRE configuration, which is usually used in a hub router in the hub and spoke topology, or by the way, we could also do it in a mesh or partial mesh as well. We can have more than one multipoint GRE interface. It's not strictly hub and spoke per se. We have a single GRE interface that's configured with multiple GRE tunnels. And in this particular case, the same subnet gets configured for all of those GRE tunnels. In order to learn about the IP addresses of the other peer, the devices that are using multipoint GRE have to use NHRP to build that dynamic GRE tunnel. And by the way, the peers can also, they don't have to use static IP addresses anymore. We can use dynamically assigned IP addresses on the peers. And it's also going to support the three different traffic types: unicast, broadcast, and multicast. All right. So we can mix and match. We can kind of have a combination of each of these different topologies. We see three diagrams on this particular slide that shows the options for implementing GRE networks using GRE or multipoint GRE. In the left diagram here, right, it's a traditional hub and spoke environment. We have a set of point-to-point tunnels using only GRE interfaces. On the hub, we need to create as many of those GRE interfaces as there are spokes. And on the spoke, we would just have to have one GRE interface to go back to the hub. All traffic between the spokes has to flow over the hub. All right? In the middle diagram, we see this multi-point GRE interface. So only a single interface is required at the hub, but we still need all of the single GRE interfaces on the spokes. And in addition, we have to deploy NHRP for the hub so that it can learn about the spoke addresses and correctly provision the spoke to hub GRE tunnels. In the far right diagram, right here, we can see that we've kind of elevated our game a little bit, and we're creating hub and spoke environments using multi-point GRE, but we're creating a full mesh. And it could be a partial mesh, but in this particular case, it's drawn as a full mesh. All right, so we would have separate multi-point GRE interfaces on each device. The benefit of this, of course, we run NHRP on all those devices, but the benefit of this is we have site-to-site connectivity, the ability to communicate site-to-site, and then, you know, we don't have to necessarily route traffic through the hub to get from one spoke to the other. All right? And actually, quite frankly, the configuration is, outside of adding NHRP on top, the configuration is pretty basic. You duplicate whatever we do on one router with all the other routers. All right?
I have a question.
Yes, sir.
So that that center one, the hub and spoke with the MGRE in the middle. So the spoke routers, they reach out to the hub, right, to get registered into that table, the NHRP table?
No, you're talking about DMVPN. And in DMVPN, we have that automatic registration. We do use NHRP on the hub router to discover the spokes. So I guess in a sense, you're correct, because the spokes have to respond to that request and identify what their IP address is.
Okay, because then I was wondering how exactly it works with the example to the very right. Like, how does one of those spokes know to reach out to whichever other hub or spoke? Like in the configuration.
You mean in a sense of the discovery? So how do the multi-point GRE devices know how to reach out?
Right.
Because we're not specifying a specific spoke, right? I mean, think about it from this. I mean, obviously, the far left, we'll kind of go through each. We know that this one, that's a simple one, right? Because everything is statically configured, right? In this particular example, we have a static configuration on the spokes, but we have essentially a dynamic configuration on the hub. Now, the question that you're asking is then, how do I know that this tunnel is created, right? Because I'm not necessarily specifying a tunnel destination. I'm discovering the tunnel destination through the use of NHRP, correct?
Okay.
No, that makes sense, right? So you're saying, okay, this spoke router has a physical IP address, and it has a tunnel interface and a physical interface. So we use NHRP to discover what that physical interface is in order for us to communicate. Does that make sense?
It does.
But how does that work if everybody is multi-point GRE, is what you're asking.
Right.
Does anybody have any idea how that works? Is there any kind of configuration on the multi-point GRE side? So what Aaron is saying is he's saying, okay, I've got a multi-point GRE interface configured here, but I'm not necessarily specifically setting the tunnel source and the tunnel destination. I'm relying on NHRP to discover that. But if
right, all it has is the private IP address range for the GRE tunnel.
Right. But remember, this is all in a common subnet. So NHRP, much like ARP, NHRP is sending out these messages saying who's on the other side of this subnet, who's running Multipoint GRE and who's on the other side of this subnet. Right?
So are we assuming all these routers are within a private network and not traversing the internet?
No, they're definitely traversing the internet. They're definitely traversing the internet. There's a tunnel interface and there's a physical interface, right? So there has to be that discovery process, and that's where NHRP comes into play.
So if I'm looking at a configuration for, let's say, the hub for the MGRE, like the tunnel interface would just have the private IP network, right? It wouldn't have anything else. It wouldn't have source destination. Well, maybe source of the physical address or physical interface that it's going to leave. But then if you look at the physical interface, it has the IP, the public IP specified, but I don't see anywhere where it would say, well, here are the other MGRE endpoints, here are the public IP so you can reach them. If all it has is a private IP network, I'm trying to bridge that gap to understand how does it know what public IP address to go to for any of these to even talk to each other?
Because it's a reverse process. We're not trying to discover the public address. The public address is being announced by the other location. So it's almost like an inverse ARP environment, right? Where when we set up the tunnel information, so we go into global configuration mode, we specify our interface tunnel, we specify that we're using tunnel mode GRE multipoint. If we're going to set up the tunnel ID, we use a tunnel ID key and network ID, and then we have to enable NHRP on the interface.
So Scott, if I may interrupt, so NHRP is the public address, it's the endpoint. That's the mapping point. So these folks have to discover that, and then all these channels will be established, and all traffic will be channeled over these circuits.
Correct.
So that's the endpoint, basically, the NHRP, which is the hub router.
Well, you can establish static mappings, right? And remember, NHRP, the goal of NHRP is to map the private IP address to the public IP address, right? Does that make sense?
That makes sense, yeah.
Yeah.
And in the case of a full mesh, and I'm going to have to look this up, but I think in the case of a full mesh, some static configuration needs to be applied in order to be able to discover those endpoints, because you're not on the spoke sides. If you're just doing a hub and spoke where you've got a multi-point GRE tunnel interface and you've got several classic GRE tunnel interfaces, remember on the classic GRE side, you're specifying the tunnel source and the tunnel destination. On the multi-point to multi-point side, you're not necessarily doing that. So,
right. So yeah, that's what I was wondering. Like, where does that static configuration go if it doesn't go on the tunnel interface? But if you said that there should be, then okay, then that would make sense.
Yeah, there has to be, and I'll have to look up that configuration. We can take a look at that.
Okay,
yeah,
cool.
And also, Aaron, I'll probably show you tomorrow something that we do from our side internally, and that is basically doing the DMVPN channels, and it will probably clear some points.
Right, and see, in this particular configuration, we haven't even set up. We haven't even really configured or identified the DMVPN aspect of this, right? So let's say, let me give you an example. Let's say we have 4 routers that we're configuring. And in this particular diagram, we've got 4 routers that we're configuring right here. Okay, so we'll call this guy router 0, we'll call this guy router 1, we'll call this guy router 2, and router 3. Okay. In router 0, I would create a tunnel interface. We'll just call it tunnel 0. Okay. And I would give it an IP address, let's say, well, I don't know, 11.0.0.1. Okay, with a /8 mask. Then I would create an NHRP map that would map an IP address to a next hop or another address. So let's say that router 1 has a physical address of 10.0.0.2. All right, in fact, let me put that on here. So this guy has a physical address of 10.0.0.2. This guy has a physical address of 10.0.0.1. And then we've got 10.0.0.3 and 10.0.0.4, respectively. Those are the actual physical IP addresses on each of the respective Ethernet interfaces that are going to the Internet. So I would create a map using the IP NHRP map command that would map the tunnel interface of that router. So in the case of router 2, I'd say, okay, router 1, sorry. So this is the physical address, and then I'd have an IP address of 11.0.0.2. That would be my tunnel interface address. So I would create, using the IP NHRP map command, a map that says 11.0.0.2 goes to 10.0.0.2. Does that make sense? And then I would specify the next hop information as 11.0.0.2, and then the tunnel source would be my Ethernet 0 interface. And then on each of the other routers, I would do a similar thing. I would say 11.0.0.3 maps to 10.0.0.3, 11.0.0.4 maps to 10.0.0.4, and 11.0.0.1 on router 3 maps to 10.0.0.1, and so on. All of these interfaces would be set up as multi-point interfaces. And then we would use the NHRP protocol to discover all of the other endpoints, if that makes sense. So we would actually see automatic discovery for all of the other NHRP endpoints. We would, if you use the show IP NHRP command, you could see that the tunnel was created between the 2 endpoints, and so on. So if we get a chance, maybe I'll kind of throw together a quick configuration and show you that configuration. We might actually see it as well when we start to get into the actual DMVPN configuration piece as well. All right. I completely understand your question, and the answer to that question is, in this environment, there is still some static configuration that has to take place. We can't just simply turn on Multipoint GRE on the interface and let it go out and dynamically discover, because how could it possibly know what it's trying to discover if I don't identify those destination endpoints? Remember, each of the physical interfaces in this environment might be separate physical IP addresses that are connected to a local service provider. So they might not even be on a common subnet.
Yeah, I think you answered the question with the NHRP map.
Right.
Mapping the private IP address of the private IP address of that
tunnel interface
network to the public IP address.
Right.
That's right.
Yeah. Okay, that answers the question. Thanks, Scott.
Somebody else was going to say something?
Yeah, I was. I'll go ahead.
Sorry, I just wanted to let you know, I'm going to shoot you over a PDF. It is an article I found online a few months ago. It does a really good job explaining how to go from a basic GRE point-to-point all the way to a Phase 3 DMVPN. It does a technical explanation, shows some debugs and everything about how to configure it and what each configuration does.
Excellent.
If you can share it with the class. So.
Yeah, well, if you can post a link in the chat window too, everybody will be able to get it from that too.
Oh yeah, I gotta find the link. I saved it as a PDF. I'll try to.
Oh, okay, okay. Well, send me the PDF and I'll put it in the OneDrive
Okay.
so that people can download it.
Yeah, it was an INE article. So.
Okay. Gates, you were going to say something?
No, I was just actually just agreeing with what Aaron said. That's basically what it is. It's just mapping the private to the public through the NHRP.
Right. And then NHRP goes out and discovers whatever else it needs to discover based on that. Okay. So the next topic that we're going to discuss in this journey down enterprise managed VPN solutions is IPSec. IPSec has been around for a very, very long time. We know that it provides things like quality connections, cryptography, based on transmission security for our IP traffic. IPSec has been around for quite some time. In fact, it was defined in RFC 4301. As part of that RFC, we offer things like data confidentiality, data integrity. Confidentiality, of course, comes from an encryption algorithm like DES or triple DES or AES. Data integrity comes through the use of hashing algorithms like Message Digest 5 or the secure hashing algorithm. Data origin authentication comes from RSA or DSA or maybe a pre-shared key. And then we also have anti-replay security services because we're able to identify whether or not, these data is being copied and being replayed in our environment. All of these services are being provided at the IP layer, which protects not only the IP layer, but also protects all of the upper layer protocols as well. All right. What happens is it enables a system to select security protocols, to define what algorithms we're going to use. It negotiates cryptographic keys that are required to provide the requested services that we're trying to transport across this IPSec enabled configuration. IPSec protects one path, or it can protect many paths between a pair of devices. And the protocol itself provides IP network layer encryption. And in order to do that, we have to have a new set of headers that have to be added to the IP datagram so that we can transport that encrypted data across the network. The purpose of those new IP headers is to provide information for securing the payload of the packet and also then in turn being able to transport that secured payload to its destination. IPSec is actually not specifically a protocol itself. It's actually a suite of protocols that provides various functions within the IPSec protocol suite. For example, IKE, which is the Internet Key Exchange Protocol. That provides the ability for us to manage keys that are going to be used for encryption or processing data securely over the IPSec tunnel. Authentication header, another kind of IPSec implementation option, allows us to define user traffic encapsulation. It doesn't provide confidentiality, but it does provide data integrity, data origin authentication, and protection against replay of the user's traffic. But does not provide for message confidentiality. ESP, encapsulated security payload, allows us to define user traffic encapsulation that provides all of those other things that provided, so data integrity, data origin authentication, protection against replays, but it adds confidentiality to the user's traffic as well through the use of encryption and encryption techniques, okay? So those are the three cornerstones, or the three major components of the IPSec protocol suite. In addition, we have a concept in IPSec called an SA. SA stands for Security Association. It's really a fundamental concept to IPSec. Both AH and ESP use SAs, and as a major function of IKE, the Internet Key Exchange, to establish and maintain the security association profiles that occur from point to point. All right, so what is an SA in general? An SA is basically just a simple description of the current traffic protection parameters, like what kind of algorithms am I going to use? What are the keys that I'm going to use? How am I identifying what traffic is going to be encrypted and what traffic is not encrypted, and so on. So all these different traffic protection parameters that get applied to our specific user traffic flows is part of this description, this SA description. If I'm using AH or ESP, protection gets applied to the traffic stream. All right. Now, a traffic stream is very rarely something that only happens in one direction. SAs are created per direction. So in an IPSec session, you actually would have 2 or more SAs created to provide protection for that particular traffic stream. To secure typical bidirectional communication between hosts, or between maybe 2 routers or 2 security gateways, we would have 2 SAs, one for each direction, to define those protection mechanisms in each direction. So let's go ahead and break down each of these individual protocols and kind of talk about IKE and AH and ESP as a progression going through this discussion of the IPSec protocol suite. IKE, or the Internet Key Exchange, has 2 distinct phases of operation: IKE Phase 1 and IKE Phase 2. Phase 1 is the initial negotiation phase that occurs between the 2 peers. It begins with an authentication. So each crypto peer, each device that's trying to verify the identity to the other device, is going to exchange authentication information. Once authentication has occurred, those crypto peers agree on what type of encryption algorithm they're going to use, what type of hashing method they're going to use, the lifetime of the cryptographic process, whether it's a data lifetime or a time lifetime, the key exchange method that's going to be used. In other words, what kind of Diffie-Hellman key exchange method are we going to use, and so on. All of these parameters get negotiated, and then the peers establish a bidirectional security association. So the goal of Phase 1 is to establish a basic security channel so that we can then start to negotiate Phase 2. Phase 1 itself even has 2 operational modes. It can operate in main mode, or it can operate in aggressive mode. And I'll talk about the difference between those 2 phases in a minute. The slide doesn't really get into a lot of detail on it, but I want to make sure you guys understand the difference between main mode operation and aggressive mode operation. Before we get into that, though, let's talk about Phase 2, right? Phase 2, the second phase of IKE, is what allows us to negotiate the IPSec parameters, or the IPSec SAs, between the matching peers, between the peers that are communicating. IPSec is the encryption phase. Oftentimes we call this the bulk encryption phase, right? The goal of Phase 2 is to establish that secure channel for the actual data exchange. The peers establish unidirectional SAs, 2 at a minimum, could be more than 2. And this Phase 2 exchange is, well, sometimes it's called quick mode exchange, but it is the bulk encryption phase, right? It's the phase that most people think about when they think of actually passing data from endpoint to endpoint using an encryption standard. All right. Now, I mentioned in phase one that we operate in either main mode or aggressive mode. Main mode has 3 two-way exchanges between the peers. Aggressive mode, there are fewer exchanges made and fewer packets made, so it's a little bit faster than main mode, but there are some downfalls to that approach, right? The reason we may choose to run main mode is it gives me a lot more flexibility on my policy negotiation. And in addition, there's an additional level of protection in main mode exchange for peer identity. It doesn't support dynamic address peers. In other words, we have to statically define peers. We can't use dynamically addressed peers, especially if we're doing pre-shared key authentication. And the reason is that dynamically addressed peers can only work with the public key infrastructure or PKI facilitated authentication. So we can't do that with main mode operations. The only way that you could potentially make it work, and I've seen this done in the past, even though it's not usually recommended, is to use wildcard pre-shared keys. But that is a very dangerous proposition, and it's not generally recommended. If we're running in aggressive mode, as I mentioned before, we get fewer exchanges made, so fewer packets go back and forth. That makes sense. It's going to be a little bit faster than our main mode negotiation. But the downside to aggressive mode is it doesn't protect the identity of the peers, because the actual names of the peers are sent over the unsecure network, the internet or whatever it might be, in plain text. All right. There is a benefit of aggressive mode. It does pre-shared key authentication for dynamically addressed peers, because now I can identify those peers because the peer information is being sent over the channel. All right, so there are pluses and minuses to either mode of operation. You just have to be aware of what those distinctions are, so when you decide what method you're going to implement, you understand what those vulnerabilities are and what the benefits are. Okay? Once we've moved on from phase one, we can move into phase two of our operation, which is our IPSec operation. Now, IPSec can actually operate in 2 modes itself. We can operate it in tunnel mode, and we can operate it in transport mode. If you look at, let's just focus right now, we see ESP and we see AH here, so we've got the 2 different versions of IPSec SAs that we can create, but if we look at just the tunnel mode versus transport mode, you'll notice that in tunnel mode, we create a new IPSec header, and that gets added to the packet header itself. The complete original datagram is encapsulated inside of ESP as payload, right? So our original header is maintained, and we're creating this new tunnel header, which allows us to route the traffic over our public domain. The downside to this approach, of course, is overhead, right? We're adding 20 bytes of overhead just with the new IP header, plus the ESP header itself, which is going to add another 56 bytes of overhead, I believe it is. I'll have to look that up, but I believe that's the correct value. In transport mode, the original header gets preserved, and all the forwarding decisions are based on the original IP header as opposed to the new tunnel header. We typically see tunnel header used, or tunnel mode, used in site-to-site VPN configurations, and then transport mode is typically used in a remote access type of VPN solution. Okay. When IPSec operates with AH, so now we're going to take a look at the comparison between AH and ESP in this case. focus on the top part here, all right, because that's what I'm going to talk about next. When we're operating with AH, transport mode protects the external IP header as well as the data payload, all right? And we see that here in the fact that authentication is really spans the entire payload. The actual authentication header goes right after the IP header, but before all of the other higher layer protocol information, okay? That's in transport mode. In tunnel mode, the entire original IP header gets authenticated. And we build a new IP header, and that new IP header is really protected the same way as the IP header in transport mode, in that authentication is applied to the entire payload. All right? But there is no encryption here. And that's the key. With AH, we're only authenticating the data. We're not actually encrypting or hiding the data from being visible across our domain, across the internet or whatever it is. Okay? If I'm operating in ESP mode, ESP means encapsulated, or the acronym stands for encapsulated security payload, but it means essentially encryption. All right, the IP payload gets encrypted with the original headers. Those get left intact in transport mode. So we extend the original IP header outside of our ESP header and our encryption. And then the only thing that gets encrypted are the upper layer protocols. And we apply some authentication to that as well with the ESP header. So we're applying authentication and encryption in this particular case. ESP doesn't actually, in transport mode, ESP doesn't actually authenticate the IP header itself. When we're using tunnel mode, the original IP header is protected because the entire original datagram gets encrypted. And with the ESP authentication mechanism, the original IP datagram and the ESP header are included, but the new header that was created that allows us to do that routing from endpoint to endpoint is not part of the authentication process. Does that make sense? I mean, I'm basically describing what you're seeing on the slide here, but you know, it kind of helps to be able to look at it and talk about it at the same time, so you can see what that relationship is. All right. All right. So why are we even talking about IPSec? Well, we know that it provides us the ability to have some sort of confidentiality or authentication, integrity, etc., as we're transporting data across the public domain. But the problem with IPSec is it has some limitations. GRE has limitations in that GRE doesn't provide any encryption mechanisms, and so it doesn't provide for confidentiality or authentication or message integrity. And IPSec has some limitations as well. All right? So if we marry these two protocols together, we can take advantages of the features that both protocols provide to give us a much more robust and secure way of communicating over this public domain. I mean, we know that IPSec provides all the security methods for tunneling data across the IP network. But the problem with IPSec is it doesn't support broadcasting. It doesn't support multicast. So we can't use that protocol. We can't use IPSec in scenarios where we have to have routing protocols or some other protocol that requires, multicast or broadcast to work. In addition, IPSec doesn't work with multi-protocol traffic. Now, GRE, on the other hand, can carry anything. It can carry broadcast traffic. It can carry multicast traffic. It can even transport non-IP-based traffic But the problem with GRE is it doesn't provide any of the encryption mechanisms. So obviously the natural solution is then to combine these two technologies together to get the benefit of both technologies. We can use GRE tunnels to transfer the traffic that we want to transfer, and we can use IPSec to encrypt the GRE traffic. All right. This provides a point-to-point configuration. So when do we usually use this? Well, we use this if we have to run routing protocols over the WAN, and the traffic has to be protected. The underlying transport can be the internet, or it can even be a provider-managed VPN, but the overlying transport is our GRE and IPSec combination. Now, when I say IPSec and GRE combined together, I'm not talking about DMVPN. I'm not talking about GETVPN. I'm not talking about FlexVPN. I'm talking about a manual configuration that combines these two technologies together. So it's not really an appropriate solution for a large number of tunnels, but because it gets kind of burdensome in much larger deployments, because remember, all of these tunnels are point-to-point. So we would look at a DMVPN solution, which, by the way, is essentially just a combination of these two, and Multipoint GRE, et cetera, et cetera. If you want to transport GRE over an IPSec solution, you can do it in either tunnel mode or transport mode. We know that tunnel mode is going to add at least an extra 20 bytes to the total packet size, but you're not limited. You can choose to use either mode of operation. If, and this is a very important concept, if you're using GRE over IPSec that's going through a NAT or a PAT device, when we're doing network address translation or port address translation, you have to use tunnel mode, okay? Because remember, we're copying that original IP, or leaving the original IP header intact. We're creating a new IP header for the routing function. All right, tunnel mode is also, by the way, required if GRE tunnel endpoints and crypto tunnel endpoints are actually different. I don't know if we'll get into that detail of it later on, but if we don't, I'll see if I can kind of talk about that. All right. Now, there are two options when we're implementing GRE over IPSec. We can use crypto maps, or we can use tunnel protection. And we see that listed on the slide, the ability to use crypto maps or tunnel mode protection. If I'm using a crypto map, the packets get routed to the tunnel interface. The packet gets encapsulated with GRE. That encapsulated packet is then forwarded based on the routing table to the appropriate interface, and then the encapsulation occurs. The encapsulated packet is encrypted using the crypto map configuration on the crypto map interface. If I'm just using the tunnel protection mechanism, the packet gets routed to the tunnel interface. GRE then encapsulates that packet. IPSec adds the encryption to the GRE tunnel, and the encrypted and encapsulated packet is then forwarded to the destination based on the routing table. All right. The configuration of crypto maps is a little bit more complex. So usually, and we see this a lot with our customers, we use tunnel protection mode, but there are situations where you may actually have to use crypto maps. Let's say, for example, you're doing the encryption and encapsulation on physically different devices. You would have to use the crypto map option. All right. Usually that's not the case, though. Usually you're just simply using the same device to provide this encapsulation process. So we're going to use the tunnel protection mode to do that. Now, I don't know if we're actually going to see this configuration, if we have time to get into doing the actual configuration. If I don't have time, guys, if we don't actually have time to go through this as part of our lesson here, I promise you that I will record lab videos that correspond to each of these chapters, and I'll post those videos on our YouTube channel so that you can actually go back and see some of those lab configurations that are associated to some of these lessons. Because I definitely want you guys to be able to see some of these configurations in operation, as opposed to just hearing the lecture part of it. Okay? All right. Another technology that's available to us is something called a VTI. All right? VTI is it stands for Virtual Tunnel Interface. And the difference is slight, but there is a difference between using an IPSec configuration and a VTI configuration. So we'll talk a little bit about that in this lesson here. It is really just an alternative to creating GRE tunnels over IPSec. Okay? The benefit of VTI is that it provides an actual routable interface. And that routable interface supports native IPSec tunneling built into it. And so that makes the configuration actually a little bit simpler than doing static GRE and IPSec configurations. It's another mechanism. We wouldn't run this in the same configuration that we talked about with the GRE and IPSec. So there are some differences, but it's something that I would run in lieu of the previous option that we just talked about. IPSec VTIs, these virtual tunnel interfaces, provide a routable interface type. And the benefit of that is it allows us to terminate IPSec tunnels, and it provides a much easier way to define the protection from site to site using, I guess, for lack of a better term, I guess I would call it an overlay, right? So kind of an overlay network, all right? The VTI tunnel supports native IPSec tunneling. It's going to allow interface commands to be applied directly to the actual IPSec tunnels. And those IPSec tunnel endpoints then get associated with the virtual interface. I keep mentioning this idea of a routable interface type, right? I mentioned it a couple of times already. Because there is a routable interface at the tunnel endpoint, we can apply a lot of common interface capabilities directly to the IPSec tunnel. So we have, I'm trying to think of how I can describe that concept so it's better understood, because this is a significant difference from what you would see with just a standard IPSec tunnel integrated with GRE. The biggest benefit, and I'll see if I can try and incorporate some of this discussion as part of this particular slide here, but the biggest benefit of the use of IPSec VTIs is in the configuration. The configuration is greatly simplified, especially when you have to provide protection for lots of site-to-site VPN tunnels. All right? The biggest benefit, because we're creating this virtual interface, this virtual tunnel interface, is that the configuration doesn't require a static mapping of IPsec sessions, to a physical interface. The IPsec tunnel endpoint gets associated to the virtual interface. Again, because this virtual interface is a routable interface at the tunnel endpoint, we apply all of our common interface capabilities directly to the IPsec tunnel. All right, we can, I mean, these VTIs can operate as regular tunnel interfaces, right? We can have one for each remote site of the VPN. Their encapsulation can be ESP or AH, but the line protocol state, right? When you do a show IP interface brief or show interface, the line protocol state depends on the state of the VPN tunnel, unlike traditional IPSec and GRE. All right. Unfortunately, we probably won't be able to see the full configuration in this lesson, but like I said, I'll try to build out a lab or perform some sort of lab configuration later on. And I'll even build out the lab files in GNS3 and provide those files in the network share so that you guys can run through some of those exercises yourself as well. Even though it might not happen this week, I'll try to do that. Okay? Because I know it's difficult. If you haven't had an opportunity to configure a lot of these features or look at a lot of these features in the actual configuration, it's kind of difficult to understand what I mean by there's a routable interface for the tunnel endpoint. And we can apply all the common interface capabilities to the IPsec tunnel, right? When you're using the VTI configuration method, we configure the virtual tunnel interface. All right. Yep, Aaron posted a link from Cisco.com for VTI configuration. I will post that for everybody. Okay. When we're using this VTI configuration, we configure a virtual tunnel interface, and then we apply our IPsec profile directly on the tunnel interface through something called tunnel protection. Actually, if you look at that link, you will see that configuration. The bottom line is it requires a lot less configuration. Crypto maps are automatically generated for each tunnel. You don't have to manually create the crypto maps like you would have to do in a traditional GRE and IPsec configuration. All right. All right. Now, there are some limitations to VTI configurations. There are some benefits to VTI configurations. First of all, using virtual tunnel interfaces is much more appropriate if you're using a small deployment, hub and spoke type of deployment as well. It simplifies configuration. I've mentioned that a few times, right? We create these virtual tunnel constructs that allow us to configure IPsec peers. So the VPN configuration compared to GRE IPsec tunnels or crypto maps is much, much simpler. All right? And if you guys have the opportunity to configure each of these, you would see the difference. Much more flexible interface feature support. With an IPsec VTI, it creates its own software-based interface, right? It's an encapsulation method that occurs directly on Cisco iOS software interface. So this feature, this function, gives us the flexibility of defining features to run on the physical interface that operates on the encrypted traffic, or we can apply features to this virtual tunnel interface that operates on our clear text traffic. right? So we can apply QoS, we can apply different functions to the encrypted traffic or the non-encrypted traffic as we need it. All right, VTIs support multicast. I don't have to say much about that. Obviously, this is going to allow the use of dynamic protocols and whatnot. IPSec VTIs need fewer SAs to cover different types of traffic. All right, so from a scalability standpoint, IPSec VTIs scale to a much more larger or more robust environment because we don't have to have as many security associations to cover different types of traffic. It also provides a routable interface. Now, I wouldn't say that this is necessarily unique to this configuration method. I mean, GRE IPSec natively support all types of IP routing protocols. We know that if we can use dynamic IP routing protocols, we can scale the design fairly well, operations are much simpler, and so on. But I don't want to suggest that IPSec VTIs are, that's unique to IPSec VTIs, because we know that GRE IPSec supports these dynamic protocols as well. All right. Unlike GRE, though, GRE supports multi-protocols. It's a multi-protocol tunneling mechanism. IPSec VTIs are limited to IP multicast, IP unicast, and don't actually support the multi-protocol function. In addition, in Cisco iOS software, stateful failover isn't supported with IPSec VTIs. We can have multiple tunnels, right? And we can rely on our dynamic routing protocols to provide us that functionality through the dynamic routing process, but it doesn't actually fail over like we can do with IPSec tunnels, native IPSec tunnels. All right. So what is a dynamic virtual tunnel interface? And how does that allow me to create this scalable hub and spoke configuration? Think of a dynamic VTI configuration much like you would see multipoint GRE configurations. We have a single dynamic virtual tunnel interface that allows me to create multiple spoke site-to-site remote access connectivity for my spoke locations. The IPSec DVTI configuration at the hub doesn't require any static mappings of IPSec sessions to physical interfaces. All of the VTIs are created dynamically from a pre-configured template, just as tunnels get created to the hub. All right. So this is almost like a dynamic on-demand virtual access interface for each VPN session. The configuration gets cloned from a virtual template configuration. That's going to include things like the IPSec configuration, iOS software features that would normally be configured on a regular interface, like QoS, NetFlow statistics, access control list, etc. That information is going to get cloned for each of the IPSec tunnels that are being created. So with dynamic VTI functionality, we have minimal configuration on the hub router in a hub and spoke VPN to create all of these various VTIs, one for each spoke router. The spoke peer initiates the VPN connection, which creates the tunnel and triggers the creation of that hub DVTI interface. Okay? So on the spoke side, we have a normal static VTI configuration that allows us to provision the tunnel to that hub. So we can't do dynamic on both sides, but it does provide the ability to create that hub or create that virtual tunnel dynamically. Kind of starting to sound a little bit like hub and spoke multi-point GRE with GRE, right? Static GRE configurations. But again, remember that this is a IPSec function. It's not a tunneling function, so this could be used in conjunction with GRE, all right? On the hub router, dynamic VTIs get created as soon as the spoke peer creates an IKE session to the hub device and starts to negotiate all of those IPSec policies. All right, so in terms of the configuration, the dynamic VTIs on the hub don't actually appear as tunnel interfaces. They actually appear as virtual access interfaces that automatically get cloned from the virtual template interface. All right, it's very, very confusing if all you're doing is kind of talking about it. This is one of those types of configurations that you have to sit down and play with, and you have to see the configuration to understand that process. And like I said, I'm going to try and go through that process for you guys. I might not be able to create all of those labs, in one day or 1 week. I'll probably try to create them over a period of time. Okay. All right. Okay. Those virtual access interfaces, if you remember, those get automatically cloned from the virtual template interface. What we put under the virtual template interface is just a common set of configurations that are inherited by the dynamic VTI. All the other parameters, all those other dynamic parameters like the tunnel address of the spoke, those all get filled in by the hub as each remote peer connects to that hub. All right? So the dynamic VTI is really appropriate for very large hub and spoke deployments. So it allows us to really simplify that VPN provisioning on the hub router. And we can use those dynamic VTI implementations in the environment where the spoke has even dynamic WAN IP addresses, because I don't have to statically configure the spoke endpoints in the configuration. The spokes simply call home and we create the virtual interfaces based on that. All right. So GETVPN, which actually stands for the Cisco Group Encrypted Transport VPN technology, works in fully meshed VPN environments, right? And when I'm dealing with a fully meshed VPN, if I'm not using a GETVPN solution, we have scalability problems, we have manageability problems, and we can't really completely facilitate this full meshed VPN configuration because of those issues. So Cisco came up with this technology that provides a solution for those particular challenges, that scalability and manageability challenge in a fully meshed VPN environment. So far, we've been pretty much talking about hub and spoke VPNs, right? We haven't got to the DMVPN concept, which is still traditionally hub and spoke, regardless of the phase of DMVPN that you're running. But GETVPN allows you to deploy a very complex, redundant, fully meshed VPN architecture. It is obviously developed by Cisco, so it is Cisco proprietary in a sense, and it offers really a new standards-based, because it is based on IPSec security model, and it uses this concept of what we call trusted group members. All right. a trusted member router or a trusted group member, which is a router that's running this GETVPN configuration, uses a common security methodology. And that methodology is completely independent of point-to-point IPSec tunnel relationships. I'll explain as we kind of go through the process. There's a lot of terminology and a lot of unique functionality that's part of this configuration process that you guys will learn as we start to go through these different configurations and this discussion about GETVPN. There are several moving parts, and we'll talk about each of these moving parts, and I'll talk about the technology. But there are group controllers, or what we call key servers, and then we have group members. Those are really the two major components of the GETVPN architecture: the group controllers, which are the key servers, and the group members. The key server, group controller, the key server authenticates all of the different group members. So it's what actually performs the admission control to this GETVPN domain. It creates and supplies group authentication keys, security associations, etc. to the group members. Excuse me. Group members themselves provide all of the transmission protection services to that sensitive site-to-site traffic, right? Now, it's not site-to-site like hub and spoke. It's site-to-site like any member to any member. So this is our member-to-member traffic that's going to be protected, and it's the group member itself that provides that transmission protection service to that sensitive site-to-site traffic. What the key server does is the key server distributes keys and policies to all of the registered and authenticated group members. It does this by distributing keys and policies from a centralized point in the network, and it shares group SAs with the authenticated group members. Now what this does is it simplifies the whole key distribution process, and the management is also simplified a lot, right? And you'll see that as you get an opportunity to kind of see a configuration and how the configuration is applied later on when I build one of the labs. Okay. Communication between the key server and the group members gets encrypted. All right, so this is another component that's unique to GETVPN because we want that the keys obviously need to be exchanged in a secure method, right? We can't just simply send the keys over in an open forum, right? So we have something called a GDOI, and the GDOI stands for Group Domain of Interpretation. All right, so like I said, we're really talking about something completely unique and something completely different than what we saw with VTI, what we saw with IPSec, and so on. There's just a lot of different components to this architecture. Okay, so what happens is that the key server and the group members have to exchange information. That information exchange is what allows us to establish the secure tunnels that are needed to protect the information. That information exchange is encrypted and secured using IKE GDOI. It's a standard-based protocol. It's part of the ISA KMP Group Key Management Protocol. ISA KMP is the Key Management Protocol, and it's designed to provide secure group communication. Okay? So GETVPN uses this IKE GDOI as the keying mechanism, and it supports two types of keys. All right? And this slide, by the way, doesn't go into any of that stuff, right? I'm trying to give you guys a kind of an overview of this topology. We see group members, we see the key server, sorry about that. We see the key server, we see the group members, but we don't really see the specific details of this exchange, okay? There are two keys that are used, right? Well, not two keys that are used, but two keys that are supported. One is called the TEK, T-E-K. All right. Now, TEK just is a fancy acronym for Traffic Encryption Key. That's obviously one of the types of keys that I might use in this architecture. The TEK key, or the TEK, that's used to protect the traffic between the group members. All right. Then I have the key encryption key, the KEK, K-E-K. That's used to protect the rekeys or the key refresh between the key server and the group members. All right. So the way that it works is that the key server distributes all the TEKs to the group members. The group members then use that TEK to communicate among the other groups, or among the group itself, the GETVPN group, to all of the other members. All right. The group member then uses the downloaded TEK to communicate and verify or create, or whatever you want to call it, all of the IPSec packets. The key server in turn, so we've got on the key server, we've got this TEK key and we've got this KEK key. Well, it's kind of repetitive, TEK and KEK. All right, the key server also distributes this KEK. The key encryption key is what is used by the group members to decrypt the incoming rekey message from the key server. Obviously, the whole point of this configuration is to ensure that we're dynamically able to create these tunnels. We can dynamically create the keying material that's used to encrypt the data from these tunnels, and the keying material is used to encrypt all the data, not only from the key server, but from all the group members, because each of these group members can then establish their own encrypted tunnel or encrypted data between the location. Okay? It's very confusing. I get it. I wish they had maybe a little bit of a better diagram in this case to describe this process, but hopefully we'll see something a little bit later on in the chapter. If not, when I'm doing my lab exercise and recording that for you guys, I'll try and go through that process again. All right. The group members themselves, right? Obviously, we know that the idea is that is to allow us to create this security parameter index or security association from one GETVPN member to the other GETVPN members. We do that through this whole GDOI process. All right. The group members themselves have to register to the key server to receive whatever policies are being pushed down by the key server itself. So all of this stuff, all the keys themselves, the policies for rekeying, the policies for encryption, is what allows this encryption process to take place. Okay? So once the key server receives registration messages from a group member, it generates the information that contains the KEK, the rekey policy, the IPSec SAs, which include all of the TEK attributes, traffic encryption policy, the lifetime, the source, the destination information about the traffic that has to be protected, the security index ID that's associated with each tech, and so on. These new IPSec SAs are then sent to the group member. Now, if I'm looking at the GETVPN data plane, the group members have all of the necessary IPSec SAs that can protect traffic being sent to the other group members. All right? I was going to try and say that a different way, and I caught myself and I said, well, is it really protecting the traffic being sent and received? And I guess technically it is, but remember, we have these IPSec SAs in each direction, right? These are unidirectional SAs. So we're trying to protect the traffic and send the traffic to the other group members, which is being protected by these IPSec SAs. All right? They will be able to decrypt the packets since they have the same group SAs, which were distributed by the key server in the initial registration process. It's very, very confusing. I get it. And we're not really getting into the weeds. I mean, we're talking about a lot of the concepts of GETVPN, but until you actually see it in function, you see it in configuration and you see the function of GETVPN, it's really difficult to kind of piece it together by looking at a very basic diagram. All right? Now, we talked about GDOI in general and what the purpose of GDOI does. It's a key management protocol based on IKE and ISAK-AMP. All right? It is really the underlying standard for GETVPN. It's an open standard. It was, as you can see on the slide there, it was developed in or standardized in RFC 3547. But what it does is it defines how we manage the keys in GETVPN. It's obviously we're dealing with symmetric encryption keys to perform our bulk encryption and our rekeying material. So we talked about this in the last slide. We use the principles to generate these symmetric encryption keys, the KEK and the TEK. The key management protocol is an extension of what we already had in IKE and ISAK-AMP. It's going to run over UDP port for 848, I believe, 848, if I'm not mistaken. But one of the major differences of the GDOI IKE function is that the SAs that are generated actually don't need to be permanent after the members have established their initial communication. Okay? In other words, these IKE SAs, these GDOI IKE SAs can quickly expire after we've already authenticated the member to the key server and obtained the group policy. Remember, we're not talking about encrypting the actual payload, encrypting the data. I am just trying to call home to the key server and say, hey, key server, what is my keying policy? What are my SA policies? What are my IPSec policies that I need to use in this GETVPN domain? Once that's done, I don't need the GDOI IKE SA anymore. So that can be left to expire after I've established the policy. All right? The second major difference, that was the first major difference, but there is a second major difference, and the second major difference is that the GDOI IKE sessions do not get established between all the peers in a VPN, right? Makes sense, because my goal here is to simply download the policy and the keys, right? Not to encrypt traffic, not to make sure we're protecting actual data that's being transferred between the sites. Okay? The sessions for the GDOI IKESA are only established between the group members and the key servers. Or, well, it could be an individual key server if you only have one, or it could be multiple key servers if you have more than one for redundancy purposes. All of the group members use the same set of session keys to protect their network traffic. In a classic IPSec VPN, each pair of peers has their own private set of IPSec SAs, and those IPSec SAs are only shared between those two peers. All right? Not what we see with GETVPN. In a GDOI-based VPN, which is a GETVPN, all of the group members use the same set of session keys to protect that network traffic. So we're not generating a whole bunch of different keys. We're not having to protect or configure a whole bunch of different keys for protection, if that makes sense. Okay? So GETVPN uses a rekey message as well. Remember, that was the KEK key, the KEK, not just the TEK. So we use a rekey message to refresh those IPSec SA session keys outside of the actual IKE session. In IPSec, we generally do that as part of the session, but in GETVPN, because we have this GDOI IKE KEK, a whole bunch of acronyms there, we actually negotiate that key refresh or the key messages in the refresh outside of the IKE session. So when the group IPSec SAs are going to expire, and you guys understand in any VPN, whether it's IPSec VPN, virtual tunnel interfaces, etc., remote access VPN, we always expire SAs over time. Well, we can expire them based on a lifetime, or we can expire them based on the number of packets or the number of bytes. So, and we do that so that we generate new keys for protection, right, to make sure that our keys are constantly refreshed. So when the group IPSec SA is about to expire, we send a single rekey message for that particular group, and that gets generated on the key server. No actual new IKE sessions get created for that rekey message distribution. We're actually sending that refresh outside of the existing IKE session. So in the case of the rekeying process, because it's a separate process from the IKE communication, we have two different ways that we can rekey the traffic. And you can see it listed here. We have a multicast option for rekeying, and we have a unicast option for rekeying. Okay? Obviously, you understand fundamentally the difference, right? Unicast rekeying is when we send unicast rekeying messages to each of the group members. The key server is going to generate a rekey message for only one or a few group members at a time. And in order to ensure that all group members receive that rekey message for the new SA that they have to establish, that message is sent prior to the old SA expiration. All right. When we're using unicast groups or unicast rekeying methods, a unicast group receives the rekey message from the key server, and then the group member sends an encrypted acknowledgement message back to the key server saying basically that the keys are received and that we're able to apply these new session keys to the IKE, the IPSec SAs that we have established. If I'm using multicast, in multicast rekeying, the key server sends out a multicast rekeys message to the group members to a specific multicast address. And I'm not sure what that multicast address is. I don't know if it's just an all multicast routers message, 224.0.0.2, or if it's a group-specific multicast. I don't remember that one specifically, but it sends out this single multicast rekey packet to the core, right? The core meaning the network. And then the core does the replication to all of the different group members. Because the group members, well, I'm trying to think about this multicast message, what address it's sent to. I'm going to have to look that up later on and see what address it's sent to. Because it's got to be a group-specific multicast. It can't be all multicast routers. That wouldn't be very secure. I'll have to look that one up. All right? Because the group member doesn't actually send an acknowledgement in this case, because it's a multicast message, the rekeys are actually transmitted a couple of different times every rekey period, just to make sure that they get to their destination. So it does generate a little bit more traffic than we would typically see with in a unicast environment. Okay. In addition, and this is a benefit, by the way, even though we're sending these multicast messages multiple times during each rekey period, the multicast transport is a lot more efficient in a large environment than a unicast method, right? Because, yeah, I'm sending the packet a few more times, but I'm only sending one multicast message a couple of different times. I'm not sending several multicast messages over and over again, all right? So this is going to reduce the load on the key server to process those rekey messages for each group member. The acknowledgments that get received from every group member still apply, but the group member doesn't send acknowledgments like we see in the unicast transport mechanism. All right? And because of that, and I mentioned this already, we send out multiple messages, usually two, at a minimum two, usually 3 messages every rekey period, to ensure that that rekeying material is being delivered to the destination. If your enterprise network is multicast capable, it is actually recommended that you use the multicast rekeying method, which is a much more scalable and much less memory and process intensive mechanism. All right. There are a couple of guidelines that I guess I should recommend with regard to rekeying. If most of the group members can only do unicast, then obviously you want to use unicast rekeying. If most of the group members are multicast and the network itself is capable of multicast, then we would use multicast rekeying. Okay? You can mix these two modes. So obviously if you say, well, most of the group members are capable of multicast, that might indicate that some of the group members are not capable, right? So you can use unicast for some endpoints and you can use multicast for the rest of the endpoints. When they say that the transport network is capable of multicast, obviously we're talking about routing, right? Switching by default is technically capable of multicast. It's not very efficient because it will actually flood that multicast traffic. But from a routing perspective, obviously in order to support this rekeying option, this multicast rekeying option, the infrastructure has to be capable of performing the routing. Okay? All right. I know it's a lot of information. I get it. There's a lot of stuff to talk about here, but hopefully you're picking up at least a little bit of this information. And as we progress through the chapter, maybe a little bit more becomes clear and we get to some of the more functional aspects of GETVPN. What are the benefits of GETVPN? Believe it or not, the configuration is really, really straightforward. All right. It is also extremely scalable, right? The configuration doesn't exponentially grow when you're adding more and more and more group members. And the key to that, and really the biggest point of that, is that you have to understand, we're not talking about a hub and spoke environment where I have some sort of dynamic multi-point interface on one side and I have some static point-to-point interfaces on the other side. This is a full mesh VPN solution. So you would expect that as the number of members grows and as the complexity of the GETVPN architecture grows, that the complexity of the configuration will grow, and it's not the case. The configuration doesn't really change that much when you're adding additional group members, okay? So it is a very scalable and a fairly simple configuration to apply. It also provides support for multicast, and we've already talked about this several times. Our VPN solutions need that multicast support. We have to have that multicast support. There are some limitations though, and we can see 3 of the different limitations listed on the slide here. VPN addresses have to be routable in my transport network. All right? This is a direct consequence of original IP header preservation. We didn't really get into the packet format of GETVPN, but in most cases, GETVPN requires the original IP header to be preserved. So that means that in most cases, that's going to prevent GETVPN from being used over the internet because we have to have that routable tunnel header outside of the other encrypted header information. The compromise of a peer, and you can probably guess why based on how the keys are exchanged and the keying materials used. A compromise of a specific peer can have a pretty detrimental effect on the security of all the peers in the group. Why is that? Because the group keys are shared. If I can decrypt any traffic from one peer, that means I'm going to be able to decrypt traffic from any of the peers. All right? In addition, the key servers play a vital role in the overall GETVPN architecture. So key servers always have to be available during the initial key exchange and the IPSec SA exchange, and during the rekey and rekey process. So not only the registration process, but the rekeying process, which happens over the lifetime of the security association. So if for some reason that key server goes down, or multiple key servers go down, or they're not reachable, you're going to have a problem establishing these VPN tunnels. All right? We can get, we know that GETVPN doesn't work very well because of the IP header preservation over the internet. But, and so you might say, well, what the heck, man? Why would I ever use this, right? Well, because it works over frame relay, it works over MPLS, it works over private or virtually private service provider VPN networks, right? And of course, in IP MPLS, we add the GETVPN functionality to provide for confidentiality and encryption and such, because MPLS doesn't provide that functionality. All right? So we're looking for that transmission protection technology that is scalable, manageable, and cost-effective, maybe because of regulatory guidelines, maybe because we have transmission protection requirements and so on. Because GETVPN is so flexible in its ability to establish these dynamic tunnels and these multi-point tunnels, we have really a parallel to simplify security over a layer 2 network or an MPLS network, even if it's operating as a partial mesh or a full mesh. And so that's the sweet spot. That's really where GETVPN really fits in to the overall solution set that we see with all these different VPN solutions. If you're designing a GetVPN network, you do have lots of deployment options. We only really kind of talked about the general topology, you know, and the key server and the member servers and the domain, etc. But we do have a few other other options or deployment choices that we have. For example, if we want to use pre-shared keys, we can. If we want to use public key infrastructure or PKI-based authentication, we can. Obviously, using a pre-shared key is a little bit simpler, but security is generally considered stronger if I'm using some sort of public key infrastructure. All right? If I'm using pre-shared keys, I can't use dynamically addressed group members. So that's one of the downsides, even though it's a simpler configuration, that's one of the downsides to using a pre-shared key configuration. I have to use public key infrastructure-based authentication if I want my group members to be dynamically addressed group members. Now, quite frankly, that doesn't happen very often, right? Because remember, we're not running this over the internet. We're running this over frame relay, we're running this over MPLS. So it's not very common to have dynamically addressed group members. But, you know, I have to mention that this is obviously something that we concern ourselves with. All right? Hold on, I'm getting. If we want high availability, we can deploy multiple key servers. This is obviously recommended because if the key server goes out or if it becomes unusable or unreachable for whatever reason, obviously the GetVPN architecture is not going to work. So we can have several different key servers in our environment. Each key server can actually be active, and it can handle requests from several group members. So we can have one key server that's the primary key server, and it gets used to update policies to the other key servers as well. So we don't have to manually configure all of these key servers at once. All right? There are some guidelines that you should consider, though, when you're implementing VPN using GetVPN. Okay? And those are listed here at the bottom of the slide, right? It's recommended, for example, that you consider GetVPN as your primary technology so that you get that scalable full mesh connectivity between all your sites. Also, if you're implementing GetVPN over the internet, you have to use routable IP addresses on all your networks that are included in the VPN. Not very practical at all, obviously. So it's not something you typically would see, but because most enterprises are using RFC 1918 addresses inside their internal networks, but I don't know. For some reason, if you do want to use this GetVPN solution over the internet, you'd have to have those routable addresses inside your network. Probably one of the biggest downsides to this solution altogether. There is no scalability issue with pre-shared keys because you have to configure a limited number of IKE sessions. But there are other criteria, and we've talked about a couple of these already, that you use to decide whether you're going to use pre-shared keys or you're going to use the public key infrastructure, right? Obviously, when you introduce the concept of PKI, you're introducing complexity of PKI in relation to getting the certificates, distributing the certificates, installing the certificates, and so on, versus using pre-shared keys. There's a downside to using a pre-shared key too, of course, right? You can have weak pre-shared keys. The system doesn't verify whether or not your pre-shared keys are adequately secure when you're implementing this in your environment. Okay? So even though we didn't get into a whole lot of detail on GetVPN, at least you have a general understanding of the differences, and that's what you guys are going to be tested on, quite frankly. Remember, this is a CCDP course. It's a design course. It is not an implementation course. Even though we'd like to see, as an engineer, I'd like to see this practically applied, that's not the purpose of this class. The purpose of this class is to give you an understanding of these concepts so that when you're analyzing solutions and you're trying to identify what solutions you're going to use in your environment, that you understand the differences between these solutions and so on. GETVPN is covered in the CCNP security from a configuration standpoint. And we actually go in CCNP security and we actually configure GETVPN and set it up and configure the key server and so on. All right. It's a little disappointing because we'd like to kind of get into the configuration and talk about it and do the troubleshooting commands and see the exchange of the messages and all that. But it's just not applicable in this case. All right. So let's talk about dynamic multi-point virtual private networks. We've got this discussion, and then we've got the FlexVPN discussion. So we're going to go a little bit longer today than we normally would. We've already been 2 hours on this topic, but I definitely want to make sure that we get through the rest of this lesson before we wrap up for today. So we're going to keep going here, okay? Now, DMVPN incorporates a lot of the features that we've already talked about. It uses GRE. It uses IPSec. It uses multipoint GRE interfaces. But DMVPN, as a technology, is designed to simplify the deployment of a very large hub and spoke environment or a partially meshed environment, okay? That's really the point, or even a fully meshed environment for that matter, right? So even though DMVPN uses a lot of the same technology that we've already talked about, there is a specific reason why DMVPN is used so widely in the deployment of these VPN technologies. And the main thing is that it enables you as a user to scale these solutions to a much larger environment. So the Cisco DMVPN feature actually makes use of multi-point GRE tunnels, IPSec encryption, next hop resolution protocol to provide a simple way to provision lots and lots of VPN peers. All right? It also easily supports dynamically addressed spoke routers in its design. So it's not that we're using brand new technology. It's not that DMVPN is its own little monster like GETVPN is or FlexVPN is. It is actually using some of the legacy technologies that we've already talked about. There are several major features of DMVPN. We see them listed here. There's what? 1, 2, 3, 4, 5, 6 listed here. Right? I'm going to kind of go through each of these in detail and give you guys an idea. All right. Number one, the configuration tasks are greatly reduced on the hub router, right? Because we're using a multi-point GRE interface, we configure only one interface to support all of the spokes that we're configuring. The other option is what we call the zero-touch deployment option. It's not really an option. It's basically part of the DMVPN configuration. When I add a new spoke to the DMVPN environment, the next hop resolution protocol provides dynamic registration of that spoke, and the routing protocol, typically a dynamic routing protocol, provides the IP connectivity. All right? So it's going to support IP unicast. It's going to support IP multicast. We talked about that before. That's primarily a function of what? GRE, right? So we can use dynamic protocols over DMVPN. Dynamic routing protocols provide us, obviously, all the scalability and automatic spoke route redistribution that's necessary to be able to exchange all the routing information. All right? DMVPN enables spoke routers to have dynamic IP addresses because we're using the NHRP protocol to register those IP addresses of the spoke routers with the hub routers. So we don't have to have static configurations on the hub. We still have static configurations on each of the spokes to point to the hub, or multiple hubs if we have redundancy. But on the hub, we dynamically learn what the spokes look like. All right? The DMVPN solution also supports hub routers behind NAT. All right? Now, it has to be static NAT. We can't do hub routers behind PAT or behind some sort of dynamic NAT configuration because we have to be able to translate to those addresses permanently, just like a server behind in a DMZ or whatever. But DMVPN supports the hub routers behind a static NAT configurations, and even better, it supports the spoke routers behind a dynamic NAT situation or a PAT situation. All right, Aaron, were you going to say something? I saw you were unmuted. Thought maybe you were going to say something. Okay, does that make sense? We support NAT, dynamic NAT and PAT behind the spoke routers because it's the spoke routers that are actually initiating that first level of communication to the hub routers. So obviously on the hub side, we have to have a static NAT scenario, and we have the dynamic NAT scenario on the spoke side. A DMVPN with dynamic spoke-to-spoke tunnels also supports partial mesh, full mesh topologies for the VPN network. Fundamentally, it's still hub and spoke, right? So fundamentally, the overall architecture is hub and spoke. But in later phases of DMVPN, we introduced the ability for spoke-to-spoke communication. We can deploy, and we saw this on a previous slide, multiple MGRE interfaces in our environment. So we're creating this kind of partial mesh or full mesh topology. All right? And by the way, DMVPN separates the encapsulation function with the encryption function. So we can run DMVPN without IPSec, which maybe saves us a little bit of overhead. Obviously, we lose all of the protection mechanisms that IPSec introduces, but it saves us a little bit of that overhead. All right? So there are two DMVPN models that are used, and I think they're pretty self-explanatory, but I'll go in and describe these a little bit in more detail. Hub and spoke versus spoke-to-spoke. In a strict hub and spoke DMVPN deployment, each branch has to be configured with a point-to-point GRE interface back to the hub. And on all of the traffic between the spoke networks have to flow through that hub router. That's more of your kind of traditional GRE with IPSec configuration. DMVPN provides scalability with this configuration on the hub router, but it doesn't facilitate any direct spoke-to-spoke communication, which in a lot of cases can be very inefficient. All right? Obviously you can understand that the hub can be overwhelmed with a lot of traffic or a lot of information if all of the traffic has to pass from spoke to spoke through the hub. We also have the spoke-to-spoke deployment option. All right? In a spoke-to-spoke DMVPN model, that requires each branch to be configured with a multi-point GRE interface so that dynamic spoke-to-spoke tunnels can be used for the spoke-to-spoke traffic. So DMVPN provides this configuration for all of the devices, and it allows the spoke devices to dynamically peer and establish optimal routing paths. Optimal routing paths meaning, hey, if I want to talk from spoke A to spoke B, I don't have to go through the hub to do that. I can simply create this spoke-to-spoke communication. All right? DMVPN doesn't immediately produce this partial mesh or full mesh it initially establishes that hub and spoke topology, right? That's always going to be our foundation. But then from that hub and spoke topology, I can then generate that partial mesh or full mesh dynamically based on my traffic patterns that are being used in the network. All right? All right. So there are some mechanisms that DMVPN uses to combine the best of the hub and spoke environment to the full meshed environment. And these are technologies that we've already kind of talked about, but we'll hit them again because, quite frankly, DMVPN is, out of all of these VPN solutions, is probably the most widely used solution that exists today. All right? MGRE. All right? We'll talk about that one first. This guy right here. Multipoint GRE. What does that technology enable us to do? It enables us to create a single GRE interface to allow us to support multiple GRE tunnels. But it does that in a way that simplifies the complexity of the actual configuration. In addition, the GRE tunnels provide support for things like IP multicast, non-IP protocols, and other multi-protocol scenarios. So we can use routing protocols to distribute routing information, to detect changes in our VPN architecture, and so on. So these multi-point GRE interfaces allow us to build tunnels between our devices and so on. We talked about that. That was something that you guys were already somewhat familiar with. The next top resolution protocol, NHRP. It's a client server-based protocol, the clients being the spokes and the server being the hub, all right, that allows the hub to act as the NHRP server. The spokes act as the NHRP clients. What happens is the hub maintains a database, specifically an NHRP database, of the mappings between the outer, right? The outer being what? The public-facing physical interface, and the tunnel, which is the inside tunnel interface of each spoke. There's always that mapping between the private tunnel address and the outer public physical interface address. So what happens is each spoke registers its public and internal tunnel address when it boots up, and it sends a query to the NHRP database for the addresses of the other spokes. This is really, really critical when I'm trying to establish spoke-to-spoke tunnels between each of the spokes. Remember, the spokes can have a dynamic physical IP address. They have typically a static tunnel address, but the physical address can change. So in order for us to maintain this updated information dynamically in real time, I'm going to use this NHRP database to map that information, all right? And that is really critical in establishing this spoke-to-spoke communication, all right? IPSec. We know what IPSec provides in this environment. It provides the transmission protection. GRE doesn't provide any types of cryptography or encryption or message anti-replay, integrity, etc. So in a DMVPN architecture, IPSec provides all of that transmission protection. Okay? Now, there are some excellent benefits to using DMVPN, but it does have some limitations. We'll talk about the limitations first, and then we'll talk about all of the benefits. All right? Number one, it requires public key infrastructure-based authentication. And that's primarily for the scalable spoke-to-spoke authentication that's required. That means that we have to implement PKI. Now, it doesn't necessarily have to mean that we're registering public certificates and going through that process of establishing this infrastructure through the use of publicly signed certificates, although generally we try to do that. we can use self-signed certificates in this public key infrastructure process. It degrades the authentication of the VPN, but it can be used. All right. A DMVPN, because it has several moving parts, can also be a little bit more complex to troubleshoot, you know, when we're comparing it to our basic IPSec tunnel configuration. Because we have to troubleshoot NHRP, we have to troubleshoot GRE, Multipoint GRE, and so on. So those limitations are relatively minor, right? Compared to what you gain from utilizing this architecture, right? Scalable full mesh VPN topologies, lots and lots of peers. The tunnels get dynamically created as they're needed. Very little configuration. The configuration on the hub doesn't change regardless of the number of peers that you add to the network. We use GRE tunnel interfaces, so we can use the advanced features like dynamic routing protocols, quality of service, security features, access control lists, etc. It can run over the internet, even if it doesn't support customer routing information, because the tunneling hides all of that internal addressing and so on. These are all wonderful benefits of DMVPN. Technically, really, they're benefits of GRE, right? But because DMVPN utilizes GRE as a fundamental principle, it's incorporated as part of a benefit for DMVPN. Okay? It is generally, like I said, and I see this in the industry today, it is preferred technology for large WAN networks. Okay? And there are, 5 different deployment examples that they give you on the slide here. I'll talk about maybe specifically what each one of these might be represented as in more of a logical representation. For example, the first one, a large number of low bandwidth spokes. What does that actually technically mean? The most common place that I've seen this, and we see this all the time, is ATMs, a bank ATM network. We have a lot of ATMs, potentially thousands of ATMs, but there are very low bandwidth spokes. They require connectivity to the headquarters, obviously, for secure transaction processing and so on. But we can connect these sites over the internet and still provide that privacy, the data integrity, and so on. Of course, this is a business critical application, so we can apply QoS, et cetera, et cetera. So that's an example of a large number of low bandwidth spokes. The small office or home office access to the corporate environment. Probably not one of the most common implementations, but you can see where this could be useful, right? DMVPN can be used to provide work access from a small office or home office. We can have a whole bunch of spokes in this case. Now, they're not necessarily low bandwidth spokes, but they can be spokes nonetheless. And they need to access the corporate environment, right? Now, the nice thing about this, because we do multicast, because we do broadcast, because we do unicast, we can support voice over IP. We can support spoke-to-spoke voice traffic if necessary. If I want to place a phone call from one small office or home office to another small office or home office, I can support that using a spoke-to-spoke voice tunnel. Okay? Enterprise extranet. Oops, I forgot my little check mark there. Okay? Otherwise, I'll forget which one I talked about. A lot of times, big companies require connectivity to business partners. We see this with banks also, right, that are doing secure financial transactions to other financial partners, right? So DMVPN can be used in this case to secure traffic between the enterprise and those partner sites as well. We can still provide network segregation. So we can say, okay, in this case, I'm not going to allow spoke-to-spoke communication. I'm only going to allow communication through the hub. And we can actually do that through the DMVPN configuration. All right, so that's an example of an enterprise extranet. Enterprise WAN connectivity backup over internet links, right? Backups, right? We can use DMVPN as a backup solution for a private WAN. Maybe I'm using MPLS as my primary WAN solution. But I want to have a cable modem, business class cable modem, or a DSL line at the office, and I want to be able to use that as a backup to my private WAN, not just for internet access, but as a backup to my private WAN. And we actually see this done quite a bit as well. So I can use that DMVPN solution as a backup to my already secure and private WAN solution that's managed by the service provider. Okay? And then for service provider VPN services, right? DMVPN allows service providers to offer managed VPN services to their client. Maybe it's a hosted firewall solution, a hosted voice over IP solution, etc. And we can even have traffic from multiple customers get aggregated into a single provider edge router, but we can still separate that traffic using VRFs, because we can incorporate the use of virtual route forwarders in this case. All right? So we'll wrap up our DMVPN discussion by talking about the different phases of DMVPN and what each phase of DMVPN added to the overall communication process. In phase 1, obviously the initial phase of DMVPN, the hub router uses a multipoint GRE interface to connect to all of the spoke routers. So we already saw this multipoint GRE technology introduced in phase 1. The spoke routers use regular point-to-point GRE tunnels, and the spoke routers can only reach the hub, and they can only go to the other spoke networks through the hub. Now, the benefit of phase 1 is a very simplified configuration on the hub. All the routers in DMVPN phase 1 use the same subnet. We have a common subnet. The hub is still acting as a next hop resolution server, so NHRP is working on the hub router. The spokes register with the hub, so they're going to announce the mappings between the tunnel IP address and the address on their physical interface, so the hub knows how to reach each of the spokes. Since that registration is automatic, it allows, again, dynamically assigned IP addresses on the spoke routers. All right? What's the biggest disadvantage of DMVPN phase 1? No spoke-to-spoke communication. And that is really literally the single largest disadvantage that we see on DMVPN phase 1. We can use just about any routing protocol that we want over DMVPN phase 1. But because it does not allow spoke-to-spoke tunnels, all the traffic has to go through the hub. That means that the next hop IP address for destination prefixes that exist on the spokes has to be the hub router. All right? So really, what do I have to configure on the spoke routers to get to every network destination in the DMVPN environment? I'll give you a hint. It's a default route, right? That's all I need, all right? I can distribute the default route through a dynamic routing protocol, maybe using default information originate or some other method through a dynamic routing protocol, or I can simply statically configure the default route on my spoke routers. All right? The other downside to DMVPN phase 1, if I'm using a traditional distance vector routing protocol like EIGRP, is I have to disable split horizon on the hub router. We know what split horizon does in distance vector, right? The point of having split horizon is to prevent routing loops, but the rule states that the router should never advertise a route out the same interface that it learns it on. That includes that multi-point GRE interface. So when we're using a dynamic DMVPN phase 1, the hub is using only one interface to connect all of those spokes. It's using that multi-point GRE interface. So when it receives the update from a spoke network, from one spoke, it has to deliver that same update out the same interface. Obviously, split horizon being enabled by default will prevent that from happening. So that's one of the caveats if we're using a distance vector routing protocol. If we're using OSPF, we don't have the issue of split horizon because OSPF doesn't use the split horizon concept. But we have to use a point-to-multipoint network type on the hub router, and even the spoke router, by the way. I don't know if you guys remember this from the CCMP class, dealing with these different network topologies or network types that OSPF uses. But OSPF tends to act a little bit differently depending on the network type. The default OSPF network type on the tunnel interface is point-to-point. So if I leave the default network type, the OSPF adjacencies will constantly be flapping between the spoke routers. If I set up point-to-multipoint network type, and I use the IPOSPF network type command to do that, OSPF treats the network as a collection of point-to-point links. Now, that's going to change timer values as well, hello and dead timer values. So you might have to specify or modify the hello and dead timers manually as well. What if I use BGP as my routing protocol for my DMVPN network? We know that we can implement BGP in two different ways. We can implement it as eBGP, or we can implement it as iBGP. The problem you run into with iBGP is that it never announces prefixes that are received through another iBGP peer. That's another loop avoidance mechanism in BGP. Remember, BGP is very much like a distance vector protocol. Even though it is classified as path vector, it's very much like a distance vector protocol. So iBGP peers will never re-announce any prefixes they learn to other iBGP peers. But problems arise when we're using eBGP. For example, the next hop attribute in eBGP. When I'm using eBGP, I have to configure the next hop self option, because eBGP peers don't change the next hop attribute if the peers are in a common subnet, meaning that the networks that are advertised by the spokes, the next hop will be the spoke IP address, the tunnel interface of the spoke, and not the hub. All right, so we have to modify that when we're configuring these peering relationships on the tunnel interfaces. Okay. When all the prefixes get up to the hub router, that router is going to announce those prefixes to the other spokes. But it doesn't change that next hop attribute. So then all of a sudden, because we don't have spoke-to-spoke communication in DMVPN Phase 1, we don't have reachability in the networks behind the spokes, since the next hop is not actually routable. Does that make sense? These are all just kind of those little caveats that you run into as you're dealing with these different configurations and different protocols. That's why it's really so important, and I tell people that they really need to focus a lot of attention on this to get your CCNP so that you understand, and by the way, that's a prerequisite for the DP, right? You have to have your route cert, you have to have your switch cert. There's a reason for that, because you learn the configuration, you learn the fundamentals of the protocols in those certifications. Here we're kind of hitting high level. In the CCNP, you get the details, right? Now, if I look at DMVPN Phase 2, in DMVPN Phase 2, this is the first time that we introduced direct spoke-to-spoke communication. All right? Those spoke-to-spoke tunnels get automatically created without any intervention by the administrator. All right? In order for this to occur, you have to have multi-point GRE interfaces, not only on the hub, but also configured on the spokes. All right? That's what's going to allow that direct spoke-to-spoke tunnel establishment, is if you have that multi-point GRE interface. When your router establishes a direct spoke-to-spoke tunnel, it is far more efficient than sending all of the traffic through the hub, because now I can send direct traffic directly to the spoke without having to send it through that hub router. All right? There is a little caveat though, and a lot of people are not aware of this. I wasn't aware of this until recently when I ran into a problem. That only applies to unicast traffic. Multicast traffic can only be sent between a hub and a spoke. You cannot send multicast traffic from spoke to spoke. Now, what does that mean from a dynamic routing protocol perspective? It means no adjacencies between routers at the spokes. So you're only going to see adjacencies between the hub and the spoke. It doesn't mean you can't have adjacencies between spoke routers. They just can't be dynamically created. You have to statically configure your neighbor relationships from spoke to spoke. All right? Now, in this particular case, NHRP, which is still used, it was introduced in DMVPN Phase 1, but it's still used in Phase 2. It's used for two separate things. All right? Just like in DMVPN Phase 1, it's used for dynamic spoke registration. That allows spokes with static IP addresses or dynamic IP addresses to register to the hub router. But it's also used for on-demand tunnel destination resolution, right? When a spoke wants to talk to another spoke, it doesn't know necessarily what the destination address of that traffic should be. So it's going to send a query to the NHRP server, which is the hub router, to identify the spoke IP address that it needs to communicate with. All right? Now, what does that mean from a routability standpoint? It means that the spoke routers have to have full reachability information, okay? Including an unmodified next hop IP address. In other words, I don't want the next hop to be the hub router like I did with DMVPN Phase 1 because all the communication had to go through the hub. I want that next hop IP address to be unmodified. Each spoke has to have a full routing table to all of the other spokes. Now that could mean a default route if I just simply have a single connection to the internet and I'm using that default route to reach the public IP addresses of the other spokes. Or it could be an actual full routing table that identifies each of the spoke destinations. Remember, these spoke destinations, the physical interface is the routing destination. The tunnel interface is the reachability information for the actual network behind the spoke. But the physical interface is the actual IP address used to reach that tunnel interface. Okay? So you can't do summarization. Now that becomes a bit of a problem if you have a really, really large DMVPN network. All right? But it's the ability to provide for that spoke-to-spoke communication is far outweighed by, or far outweighs the lack of being able to do network summarization. All right? If I want to use EIGRP within Phase 2, we still have to disable split horizon on the hub router. That's going to allow that hub router to send updates that are received on the tunnel interfaces of the spoke routers themselves. We also need to disable the next hop self option on the hub router. Normally we talk about that next hop self feature when we're discussing BGP, but it actually exists in EIGRP as well. And we have to disable that feature on the hub router. That's going to tell the hub router to set the next hop address to the IP address of the spoke that's actually originating the route behind the spoke router. So when all the other spoke routers receive that route, they're going to see the IP address of the tunnel interface on the other spoke router as the next hop address for that destination prefix. I use that tunnel interface to query the NHRP server to identify what physical address I use to establish the dynamic tunnel spoke-to-spoke connection so that I can create that direct spoke-to-spoke tunnel. Okay? OSPF as we mentioned before, operates with network types, right? There's like 5 different network types that we see in OSPF. In DMVPN Phase 2, DMVPN Phase 2 looks pretty much like a LAN segment. So it's a broadcast network type. So if we want to use OSPF as our routing protocol, we need to make sure that we configure the routers to behave like they're connected to a LAN. All right? Now, it's not going to automatically detect that network type when we configure DMVPN. So we actually have to go in and specify the broadcast network type on all of the routers. We can use non-broadcast, which I don't know, I wouldn't personally recommend it, but we can use non-broadcast, but that means that you're going to have to go and statically configure all of your neighbors. All right? If I'm using DMVPN Phase 2 in a point-to-multipoint environment, where all the traffic has to flow through the hub, I have to be concerned about this broadcast network type, because we know in OSPF network type of broadcast, there's going to be a DR-BDR election. All right? The hub router needs to win that election every time. All right? Now, generally the recommendation is to just go ahead and set the priority of the hub router, and that's something we do on the interface, to a high value. It goes all the way up to 255. All right? But that wouldn't be the only thing I would do. I would actually go on all of the spoke routers, and I would set the priority of all the spoke routers to 0, which, if you guys remember from your CCMP class, ensures that the spoke routers can never become a DR or a BDR. Does that make sense? All right. Now, you could potentially configure multiple hub routers to act as DRs and BDRs, but usually we only have a single DR. All right. When a spoke wants to send traffic to the network on another spoke, spoke-to-spoke communication, it's going to check its routing table. And we know that routers route based on next hop IP. In the case of DMVPN Phase 2, that next hop IP address in the routing table points directly to the other spoke router's tunnel interface. Okay? Not the physical interface, the tunnel interface. All right? The problem that we have is that there is no tunnel established between those two routers because they're spoke routers. There's always a tunnel between the spoke and the hub. That always exists. But for the spoke-to-spoke communication, that tunnel needs to be created dynamically. Okay? So here's the process. The spoke sends an NHRP query to the DMVPN hub to resolve the next hop IP address of the tunnel endpoint address. Now, that next hop IP address is the physical IP address, the public IP address, to reach that particular spoke that corresponds to the tunnel endpoint address. Remember, this NHRP server has a mapping for all of the spokes because they all registered initially, and we stored those mappings during that initial registration of the spokes to the hub. So the NHRP server, the hub, is going to send a reply to the spoke routers with that correct mapping. All right? So far, so good? Kind of getting what I'm putting down here? It's a very basic process, but it's obviously fundamental to this spoke-to-spoke communication. The spoke router receives the NHRP response from the hub. That response triggers the IPSec process to establish the spoke-to-spoke tunnel. So obviously the first step is going to be to encrypt the data, right? Create that IPSec tunnel so that all packets go directly from spoke to spoke and they're secure. All right? And this traffic can now pass. However, it only passes in one direction because we didn't establish a bi-directional tunnel. Remember, IPSec always establishes a unidirectional SA between the endpoints. So guess what's going to happen? In order to get bi-directional connectivity, the other spoke needs to go through the exact same process. It needs to get the next hop information. It needs to send an NHRP query. It needs to establish that tunnel by sending an initial packet after the mapping is in place. Okay? And then then we have that bi-directional communication process. Does that make sense? Hope so. All right. So what did DMVPN Phase 3 introduce? I mean, it sounds like everything that we've talked about is pretty much what we need for DMVPN to work.
Are you up?
So we said that DMVPN Phase 3, very similar to Phase 2. It's going to allow that spoke-to-spoke tunnel, but there are some scalability issues that exist in Phase 2, and that's really the purpose of Phase 3. And Phase 3 is not really necessary unless you have a really, really large DMVPN network. All right? So all of the initial configurations are pretty straightforward. In fact, they're very similar to DMVPN Phase 2. The spoke router registers the tunnel and all the outer IP address mappings to the hub router using NHRP. That registration allows the hub to dynamically discover all the different spokes. And then after that initial connectivity, the hub and the spoke can establish its routing adjacency, et cetera, et cetera. Very much like we see in DMVPN Phase 2. In DMVPN Phase 2, though, the hub routers have to preserve the next hop IP address when they're sending the route information to the other spokes. We talked about that because if I want to establish that spoke-to-spoke connectivity, I need to make sure that that next hop information is preserved. However, in DMVPN Phase 3, the hub router doesn't actually need to preserve the next hop. We can also use summarization or even a default route to communicate. This is really the biggest difference. And this is where we gain a lot of scalability because the routing tables don't have to be huge for a large number of spoke destinations. All right, I'm hoping we'll see a diagram of this in a little bit. I'm guessing that we will, but this is the biggest difference, right? The ability to use summarization or default routes to reduce the size of a routing table on the spoke routers in a really large DMVPN environment. So, if you have 20 or 30 or 40 different endpoints, maybe you don't care, right? Because most routers can handle 20, 30, or 40 different routes. But if you have potentially thousands of endpoints, where might we see something like that? ATMs, right? Now, granted, ATMs don't generally do spoke-to-spoke communication, so Phase 1 might work very well in that case, but we don't get that ability to do the summarization or the default routing. When the spoke router, well, actually, before I get into that, this brings up another question, though. What happens when the spoke router wants to talk to another spoke and the routing information is not preserved and the routing information is summarized? Okay? It works very much like fast switching. I don't know if you guys remember, there's process switching in a router, there's fast switching in a router, there's Cisco Express forwarding, okay? In fast switching on a router, the initial packet goes up to the control plane. And then after that control plane function is processed, we build caches to fast switch all the remaining traffic through the data plane. In DMVPN Phase 3, it's a very, very similar concept. When a spoke router wants to send an IP packet to another spoke router, the first packet gets sent to the hub. Because the hub is summarizing these routes, and it could be a /16 for my entire DMVPN network or whatever. So that initial packet doesn't know how to reach the actual spoke destination. So that first packet goes to the hub router. The router then forwards that packet to the correct spoke because the hub has, because of the NHRP registration, has complete visibility of where all these spokes exist, where all the networks exist, et cetera, et cetera. Okay? In addition, the hub sends a message back to the originator of the traffic with something called an NHRP redirect. That message tells the originator of that traffic that the forwarding that it's presently doing is suboptimal. In other words, don't send the junk to the hub. It should be sent directly to the other spoke. So that NHRP redirect contains the destination IP address of the original packet. Now, the spoke sends the NHRP request for the original IP address using its routing table, and then that request traverses the hub router, then it gets forwarded, that request gets forwarded to the correct spoke router. That is the other big difference, obviously. All right? When the other spoke, we haven't finished the process yet, because remember, this is unidirectional, so we have to do this in both directions. So when that other spoke receives the NHRP request, it responds directly to the originator of the packet. And in that response, when that response goes back to the originator, it now knows the outer IP address of the destination. It rewrites the NHRP table with the correct information that stays cached for a period of time, and so on. So what I described was this diagram here, right, of step 1, step 2, step 3. Okay. Step 1, of course, was that initial packet that got routed through the hub. Step 2 was the resolution, the redirect, and so on. And then step 3 was the spoke-to-spoke communication. Does that make sense? You see the difference that we have here? Yes, the initial communication is not efficient. It's suboptimal. We're sending a lot of packets to the hub initially, but it allows me to greatly reduce the, well, quite frankly, the overhead, right, of having to know all these destination routes in my routing table, because I can use default routing just to point to the hub or point to the internet, and then the hub will handle all the redirects directly. Okay? It's kind of cool, that concept that they introduced. Again, you're only going to gain the benefit of using DMVPN Phase 3 if you have lots and lots of DMVPN spokes or lots and lots of DMVPN endpoints. All right? Because the hub doesn't need to preserve that next hop information, we can use route summarization, we can use default routes, and like I said, that's going to really lessen the impact that we're going to see on our spoke routers. If I want to move from DMVPN Phase 2, which most likely most of you guys are using, and I want to move over to DMVPN Phase 3, we probably want to use EIGRP as a routing protocol. And then we can use OSPF, of course. We can use BGP, but if we are using EIGRP, there are a few configurations that have to be changed, right? For example, we talked about this, the next hop self configuration that we had in DMVPN Phase 2, that has to go away, right? It's not needed anymore. Split horizon still has to stay disabled because we're still sending traffic through the hub, but then we can use the IP EIGRP summary commands to reduce the number of routes that show up on the DMVPN spokes. We're not talking about routes to the public IP addresses of the spoke routers. We're talking about the routes behind the spoke routers, the subnets that I'm trying to route to, okay? If I want to migrate from DMVPN Phase 2 to Phase 3 and I want to use OSPF, the network type needs to be changed to point-to-multipoint on all of the hubs and the spokes. We don't have to worry about priority configuration because in point-to-anything, right, you have point-to-point, you have point-to-multipoint, you have point-to-multipoint non-broadcast. Those are the three network types that have point in them. There is no DR-BDR election in those network types. There's a DR-BDR election in broadcast, but there's no DR-BDR election in any point-to-multipoint or point-to-point configuration. So let's take a look at a quick case study. We have a company that has several hundred branch offices in this case. The departments are using common branch infrastructure components. We want to maintain or isolate the traffic between the different departments, meaning DLANs, etc. But the current solution that we have in place doesn't really do that. All right. So we're going to take a look at really how do I facilitate this configuration. Now I have to fill in some gaps here, right? We need to know what our WAN consists of and how the physical topology looks. Let's assume in this case that the WAN has a central site and then we have several hundred branch offices. The central site has two routers, even though we only see one on the diagram here. All right. We're going to go ahead and say that the central site has two routers. That's used for aggregating all of the WAN connections on our network. Obviously, we know that those two routers are then going to be connected to our enterprise network to give us connectivity to other parts of the enterprise, our voice servers, our database servers, our data center, etc. Another common scenario, the branch offices have one router. Pretty common. The ISP at that location provides connectivity between the branch offices and the central site. All right. Now each tunnel gets protected with IPSec. We know that that's going to happen. There are two GRE tunnels from each branch office to the central site. Again, not drawn on the diagram, but if I was to implement this myself, I would want to make sure that I have multiple hubs for redundancy. Okay, so let's assume that we have two tunnels. Only one is drawn on the diagram, but we have two tunnels from each branch office to the central site. One tunnel is my primary tunnel. The second tunnel is my secondary tunnel. How would I ensure that one tunnel is used over the other? I use a routing protocol, right? So maybe I'm implementing EIGRP in this case. And I use my EIGRP to select which tunnel is going to be my primary and which tunnel is going to be my secondary. Each branch office obviously is going to have users. We're going to have services that are running for departments. And we're using access lists or some other method to limit connectivity between those segments, right? Segments could be VLANs, and then we have ACLs or some sort of filtering policy that disallows communication between those segments. All right. Now the segments are separated, but we still have to have the ability to pass traffic from one segment to the other because not all the traffic is filtered. Only some or certain types of traffic is filtered. All right. So we have to allow access for that particular traffic. I'm just kind of building this scenario. Quite frankly, I'm basing it on one of our existing customer deployment models that we have now. This is a very common case study. All right. Now, if I was tasked with this responsibility, or if I was tasking one of my engineers with this responsibility, I'm going to say, hey, we might have to add a bunch more branches in the future. So the solution that you put into place has to be scalable, number one. I don't want the configuration to be complex. I don't want, if I add a bunch of branches, for the configuration to exponentially become more difficult. All right. I still want to be able to isolate traffic between the departments. I want a security policy that I'm developing that identifies how that traffic is isolated, but I want that security policy to be centrally managed, which is a pretty common thing. All right. Now, again, we have two routers at the central site. We only see one router in this case study because really the second router's configuration is going to be identical to the first router's configuration. So just to make things simple, we only see the central site. But if you can imagine, there's a second router here, and we have a duplicate set of tunnels that go to each of the branch offices. Okay? Now, we already have a solution in place. This is kind of the current WAN implementation, and that's what's being depicted here. That is a point-to-point GRE IPSec configuration. The problem with this design is that when I add a new branch office, I have to configure a new tunnel interface on the hub router and on the spoke router. Because I'm adding hundreds of branch offices, the hub router configuration becomes, as Trump would say, huge, right? The configuration gets very long and it's hard to maintain. Guess what? We're thinking about implementing DMVPN, hence GRE DMVPN case study, okay? We already know the benefits of DMVPN. It's going to reduce the configuration load on the hub router. We only configure one interface to support all the spokes, zero-touch deployment, yada, yada, yada. We talked about all of that, all those concepts previously. We also get the NHRP protocol to provide dynamic registration of the spokes, and routing protocols provide our IP connectivity between the sites. All right? We have a highly available solution because we have two hubs, essentially. So we're going to do a dual hub, single DMVPN cloud. All right?
Hi, Scott.
Yes, sir.
If I may interrupt, have you actually automated this before? Have you done the IWAN, ACI, and just
I have not automated it. I've configured it manually, but I haven't used the ACI to configure it automatically.
Okay. Yeah, just wanted to know if you have any examples, because we looked at that before, and we did the proof of concept at Cisco, and we did our own lab in there. Just wanted to know if you have done it before, so you can share with us.
Yeah, I have not, but we will talk about ACI and APIC EM and all that stuff a little bit later. Maybe we'll see some correlation to that and this configuration. And of course, if I have an opportunity to kind of lab it out and demonstrate that concept with you guys, I will, even if it's something that I record later for you guys. But personally, I have not had experience with that. Okay?
Thanks.
So as I said, we've got two DMVPN hubs. We're not going to configure separate DMVPN networks. We're going to do a dual hub, single DMVPN cloud. That's typically how it would be configured anyway. So both routers at the central site, they're going to be hub routers for the same DMVPN cloud. Each router is going to have its own multipoint GRE interface, but only one interface is needed, as we talked about, which obviously makes the configuration from several hundred different separate tunnel interfaces to a single interface much better, much more preferred. Okay? And we're going to make use of the dynamic registration on the spoke routers. To migrate the branch routers to the DMVPN cloud, the first thing we have to do is we have to configure the multipoint GRE tunnel interface. We need this mode. Even if we're not doing spoke-to-spoke communication, maybe we're doing DMVPN Phase 1, I hope not, but maybe we are. But even if I'm not allowing spoke-to-spoke communication, I need a multipoint GRE tunnel interface on the spoke routers because I have two hubs. All right? So, and then of course we're going to overlay IPSec on top of this. We already have pre-shared key implementation, but we're planning to migrate, in this case, to public key infrastructure so that we can do our peer authentication using PKI. All right? And again, I'm just kind of guessing here. We don't see all of that on the slide, but this would be kind of a standard configuration. All right? Now, once we've decided that we've upgraded our transport network, we have to move forward with the traffic isolation at the branch office. Quite frankly, because we're using DMVPN, because we're using IPSec, the best way to isolate the traffic at the branch office is to use a VRF. All right? Hopefully our router supports this VRF technology. With a VRF, we can completely isolate the traffic forwarding between the departments. All right? Because we can identify how routes are shared between the virtual route forwarding instances and so on. All right? So let's say that we've decided that we're going to go ahead and create a single VRF. In fact, let me move on to the next slide here because that's what I'm talking about. Let's say that we've decided to create a single VRF, one for each department. And we put interfaces that are acting as the gateways for the hosts on those specific VLANs into those separate VRFs. This is what allows us to isolate the traffic between the departments. Okay? Now you could do it with VLANs and you could do it with access control lists and other aspects, but this is probably the simplest way because we are talking about a route routing. All right? But it will add some complexity, and I'm going to talk about what that complexity is as we move into the next slide here. Okay? And that would be this slide right here. So we've successfully created or upgraded our infrastructure to support this DMVPN environment. We've isolated the traffic from the different departments, but now we need to figure out how to forward that traffic between the VRFs. And this is where MPBGP comes into play. All right? Remember, one of the requirements that we initially stated is that I want to be able to centrally manage what traffic can pass between the VRFs. Now, if I did VLANs and access control lists, that would be locally managed on the branch side, and that doesn't meet my design requirement. All right? So in order to be able to do this centralized management, I have to forward the traffic to the central site, perform my security checks, my whatever I'm trying to filter or apply, my filters, before I forward the traffic back to the branch site. The solution that can allow us to do this is a layer 3 MPLS VPN. We know that because that's how we spent quite a bit of time talking about that design model. That is how service providers isolate traffic between different customers. In this case, we're not trying to isolate traffic between different customers. We're trying to isolate traffic between different departments, but it's basically the same concept, isn't it? All right? So if we implement our own layer 3 MPLS VPN solution, that's going to allow us to transfer the traffic that's isolated from each other. All right? Because we're basically going to have a separate routing table for each department. The only way that I can support this design model is to implement VRFs and have a separate VRF configured for each department at the central site on the hub router. And then we're going to use the same concepts, route distinguishers, route targets for the VRFs. We're going to transfer the routes from the branch office to the central site using MPBGP, which creates those VPN v4 routes to identify those unique subnets. Remember, traditionally VPN v4 was to allow us to separate clients and in even maybe overlapping subnets or overlapping networks. It doesn't have to be the case here. All right? It doesn't have to be the case here. Okay? So we're going to use an external BGP relationship between the central site and the branch site. Each branch office has its own internal autonomous system number, private, we obviously don't need public ASs, and so on. So now you're starting to see that we're building out this same robust MPLS VPN architecture over our DMVPN network. Okay? Now, does that mean we actually technically have to use MPLS VPN? I guess it doesn't. It depends what the infrastructure looks like. But this might be something that you implement over a service provider MPLS VPN anyway. Okay? And you control the VRFs and what routes go into what VRFs and so on. All right? We're going to use MPBGP policies to allow us to select which hub router would be the primary router, which hub router would be the secondary router. And then we announce all the routes to the central site from the branch office to create this database of dynamically learned routes at the central site. We want the central site to be able to see everything. All right? So we've connected our hub routers to the switch at the central site. We have a trunk going from that switch to the routers, and we have different VLANs to VRF mappings to match the different subnets to their appropriate VLANs. In order to provide connectivity, we've implemented router on a stick on the hub router, and that allows us to isolate traffic between the VRFs at the central site. We can see that here. A trunk interface that's connected to the switch, and then we have a security policy implemented between sub-interfaces. They have a firewall there, but it doesn't have to be a firewall. It can be a router. Okay? In this case, it is a firewall, and that's, by the way, where we would perform our security check. The firewall is connected to the switch using a trunk and sub-interfaces. We have one sub-interface per VLAN, and we use that to provide connectivity from the hub routers. All right? So the security policies get applied on the sub-interfaces, and that's what's going to allow us to control the traffic that's going to pass between the VRFs, what traffic is allowed, what traffic is denied. We can even do traffic inspection if we want to do traffic inspection. Seems like a very complex design, but a huge amount of flexibility here. I'm not saying that this case study really applies to every environment, because you may not have the need for centralized policy control, and you might just use localized policy control on the VLAN interfaces at the branch site. All right? But what this solution provides is it gives you the ability to provide traffic isolation on the branch office, but allows you to centrally manage those security checks. So when I send traffic from one department and it's destined to another department at the branch, it does go through that central firewall. That could be a downside too, right? Spoke-to-spoke communication. Actually, we're not even talking about spoke-to-spoke communication at this point, right? We're talking about intra-spoke communication. That traffic has to flow through the central site. All right? So what do we get from this? Well, the traffic's isolated between the departments. Configuration reduction at the central site because we're using a DMVPN with a multipoint GRE interface. The zero-touch deployment for the branch offices, and our centrally managed security policy. All right? The only major downside to this, I suppose, would be that all the traffic has to traverse the WAN and gets hairpinned and goes over the WAN twice before it's actually forwarded from one branch office to the other. So that makes it a little bit more complex. And the policies are obviously more complex because now you're implementing MPBGP, you're implementing VRFs, et cetera, which are not really part of DMVPN, but are necessary for this particular case study. All right.
Scott, what do you mean by hairpinning?
Well, in this case, here, this traffic is within the same branch. We'll call it just branch 1, okay? But this guy's in the HR department, this guy's in the sales department, all right? If I wasn't concerned about security between those two VLANs or between those two departments, we could just simply pass that traffic locally over a local switch and not worry about it. But in this case, because I'm trying to isolate this traffic, even though I'm allowing this traffic to pass, my policy is centralized. I'm allowing that traffic to pass based on a centralized policy that's configured on the firewall. So the traffic is leaving the site. It's being routed through the firewall to check the policy. And because the traffic is allowed, it's being sent back to the same site over the same WAN connection. That's what hairpinning is. Hairpinning is, I mean, it's kind of, you can see it right here. That looks like a hairpin, doesn't it? You know, whatever, you probably don't use hairpins, Gaith, but, you know what they are, right? So we're doubling the...
That wasn't me, actually.
Sorry?
That wasn't me. You mentioned my name, but...
Oh, I'm sorry.
Yeah, that's fine.
Was that Fernando that was asking that?
Yeah, it was.
Sorry. Did I answer your question, Fernando?
Yes, you did. Thank you.
All right. You're welcome. Okay. All right. Now, we did say in our solution in this case study that we also had multiple hubs. Okay. Now, Aaron and I talked about this. If you want to really keep it kind of simple, although the configuration is a little bit more complex, you can run a dual DMVPN cloud, right? Basically just two separate DMVPN configurations. It doubles the configuration that you have on the spokes, but the hub routers are pretty simple configurations. And then you just use a dynamic routing protocol or static routing or whatever it is to decide which DMVPN device you're going to communicate with, okay, as a primary and secondary. The option that we talked about in our case study was to do a single DMVPN cloud with redundant hubs, all right? And obviously the configuration needs to change a little bit if we're using a single DMVPN cloud. All right. You can actually have more than two hubs. You can have 3 hubs, 4 hubs, 5 hubs, or whatever. But typically, for most typical deployments, you're going to have a dual hub deployment. In both topologies, 2 hub routers get deployed for redundancy. Right? We're trying to provide high availability by using a second hub router, which could be in the same DMVPN subnet as the primary. That's our single DMVPN cloud topology. Or the second hub router can have its own DMVPN subnet, which is our dual DMVPN cloud topology. In a dual hub single DMVPN and in a dual hub dual DMVPN, say that 3 times fast, we rely on our routing protocols inside the tunnels to determine what path we're going to use. So in both cases, we're still relying on our routing protocols to identify which primary path we're going to use. Obviously, the difference between the 2 topologies is more apparent on the branch router than it is on the hub routers. With a single DMVPN subnet, the branch router has a single multipoint GRE interface, and both hub routers are mapped to this tunnel through the multipoint GRE interface. And that's what we see here in this example, right? Right here, okay? In a dual DMVPN topology, the branch router has a unique tunnel interface pointing to each unique head end at the hub. All right, so we create essentially a second GRE interface. The standard routing protocols, EIGRP, BGP, OSPF, these are what we're going to use to determine what router is the active hub over whatever topology that we're going to use. And it's the same concept for both topologies. However, in the single DMVPN topology, the hubs appear to be 2 different next hops using one multipoint GRE tunnel interface. In the dual DMVPN topology, the hubs appear to be 2 different next hops, with two different GRE or multi-point GRE interfaces. All right. So Hub 1 and Hub 2 in the single DMVPN cloud topology, you're going to see a single next hop, right? Well, there's two different next hop values, but they're mapped to one GRE tunnel interface. In both cases, we have two different next hop values. It's just a matter of whether they're mapped to a single interface or each next hop is mapped to a different tunnel interface. In general, a single DMVPN cloud is really the best, especially if you're doing dynamic spoke-to-spoke tunnel configurations, because the spoke-to-spoke tunnels can actually be built only within a single DMVPN cloud. We can't actually pass spoke-to-spoke communication across DMVPN clouds. So with a dual DMVPN cloud topology, it's easier to create the hub and spoke only environments, but it's very difficult to maintain the spoke-to-spoke environments. All right? And the primary reason for that, by the way, is that the router receives routing information from the hubs on completely different tunneled interfaces. Now, either cloud topology can be configured for either style of network. You can do hub and spoke only, or you can do spoke to spoke, right? But you'll run into problems if for some reason some spokes are talking to one hub and other spokes are talking to another hub in that dual DMVPN cloud topology. All right? So I don't know that I would say one is better than the other. In my experience, having a single DMVPN cloud is probably preferred, but there are probably scenarios where a dual DMVPN cloud might be utilized. All right, so obviously we spent a lot of time on DMVPN. Another option is to run secure socket layer. Secure socket layer or TLS, they're kind of the same thing. Obviously, TLS is SSL is the predecessor to TLS. But in secure socket layer, we typically will see this for remote user access or remote VPN access to our enterprise network. I don't have to really get into a whole lot of details about SSL VPN. I'm sure you guys are somewhat familiar with SSL VPN, but we have three modes of operation. We can see them kind of depicted here. Clientless mode. In clientless mode, we get secure access to our private web resources by going into a browser and then connecting and authenticating through a browser interface. The downside to clientless mode is that we don't get native application support a lot of times. We have to set up some sort of Java applications to do smart tunnels and whatnot through the web interface in order to support native clients on the computer. Clientless mode is great though if you are working from a kiosk computer at an airport or a coffee shop or whatever, and you don't necessarily have the ability to install a client. A more common method would be to use a thin client. Thin client extends the capability of all those cryptographic functions that we had with the web browser, but it enables access to all the TCP-based applications like POP3, Telnet, SSH, etc. Because the remote user downloads this Java applet by going to a web page or clicking on a link that's provided in whatever web portal, and then the Java applet allows us to act as a TCP proxy, if you will, on the client machine to allow us to service those TCP sessions through that gateway as a proxy connection. Probably the most common that we see from a Cisco environment is full tunnel mode, where I'm actually running a client itself on the device. Typically, it's going to be a Cisco AnyConnect VPN client for SSL. And what full tunnel mode provides is a lightweight, right? It's not a really heavy application, but a lightweight easy to configure, kind of easy to use tunneling client that provides network layer access to all of the applications on the client and at the enterprise site, because we're actually creating a full, I won't say IPSec VPN tunnel because that is not what it is. It's an SSL VPN tunnel, but it allows local application support. Okay? Obviously, there is a whole lot more that we can talk about with clientless and client-based remote access VPN. And you will get that information if you ever decide to take our CCNP security class. Aaron, I think you've gone through that class before, but that's a long class. It's 14 days. We split it up into 7 days, and there are 4 different courses incorporated into that. One of those courses is all about remote access VPN. All right, specifically with the ASA and Cisco iOS routers running that technology.
Is that coming up? Is that a class next year, or?
We actually have our first one is scheduled for January. And the way that we do that is the CCNP security is 4 different exams. And people can't get off 4 days or 14 days to take that. So we break it up into 2 parts. We do part 1, which is SENSS and SIMOS, which is the ASA stuff. That's a 7-day class. And you do 2 of the certifications. And then we do part 2, 6 months later or something like that, that covers the SITCS and SISAS, which is the ICE and all the other threat detection, ESA, WSA, and all the other tools that Cisco provides. So I can have Mike send you over some information on that if you're interested.
Thanks.
All right. Okay. FlexVPN, the last topic of this particular module. That's a 3.5-hour module. Wow, that's long. Okay. So if we're deploying IPSec VPN over our network, we know that it can be kind of challenging, right? What kind of technology do I choose? Do I choose GETVPN? Do I choose DMVPN? Do I choose Multipoint or DMVPN Phase 1 or Phase 2 or Phase 3? So, or do I choose VTI-based solutions? It's really difficult to decide which model suits your environment. So this is essentially the latest technology that Cisco has provided to kind of solve that problem, right? FlexVPN was created by Cisco to simplify the deployment of VPNs and to integrate multiple solutions together. So maybe you don't choose a specific VPN technology because you have to support all types of users. You have to have remote access users. You have to have small office or home office users. You have to have physical sites that you're connecting to, site-to-site VPN, mobility users, etc. Now, I said that Cisco came up with this, but in reality, it is a standards-based encryption technology. Cisco was heavily involved in developing this technology, but it is not Cisco proprietary. It is a standards-based encryption technology. The cost savings and the reason why a lot of companies are looking at this technology now is because they do have to support different types of VPNs. They have to support GRE, crypto VPNs, VTI VPNs, etc., etc. Because FlexVPN is open standard, in fact, it relies on IPv2, which is our next generation of encryption technology, as a security foundation. It provides all of the enhancements that are required for high levels of security and these next generation encryption protocols, what we call NGEs. All right. So it provides a transport network just like all of the other VPN solutions that we've looked at, right? We can deploy FlexVPN over the internet, over private MPLS, over frame relay, whatever it is. So we have a lot of flexibility in that case. It is designed for the concentration, and this is the real differentiator between GETVPN and DMVPN. It is designed for the concentration of site-to-site VPNs as well as remote access VPNs, using one VPN deployment that can accept both types of connection requests at the same time. GETVPN doesn't do that. DMVPN doesn't do that. Those are solely used for site-to-site VPN configurations. Okay? FlexVPN even has 3 different kinds of redundancy models built in, right? We can do dynamic routing protocols to provide redundancy using reachability information through dynamic routing protocols. We can use IPv2-based dynamic routing distribution. We can do server clustering, which is something that was introduced in IPv2. We can use IPSec, active standby stateful failover between 2 different chassis. That's a feature that's built into IPSec and IPv2. FlexVPN provides compatibility with any third-party VPN vendor that supports IPv2. So that would include, native VPN clients that are installed on your iPhone or on your Google Android devices or whatever. So there's a lot of flexibility there, hence the term FlexVPN, obviously. It supports multicast, just like our other VPN solutions that we talked about. But one of the things that it adds is an architecture for hierarchical QoS, meaning that we can apply QoS on a per tunnel basis or even on a per SA basis. We couldn't do that in any other VPN solution. All right? It works with VRFs, it works with encryption network policies, split tunneling policies. We can use AAA, we can use Radius as part of the configuration for remote access authentication and peer-to-peer authentication and so on. So it has all that integration capability, and it works both inside of VRFs, and we can use VRF assignment policies with a AAA server to isolate traffic further in that regard as well. Okay? So it offers a lot of functionality and a lot of features. I don't know that we'll get into in the next 3 slides all of those details, but again, that's not really the point of this discussion. We learn all about FlexVPN in the CCNP security class. We actually learn about the implementation. Okay? We know that it provides site-to-site connectivity. It provides remote access connectivity. It supports hub-and-spoke environments. It supports partial message with spoke-to-spoke communication, all of that stuff. All right? But it uses a modular framework for the implementation. All right? So we have tunnel interfaces that are backwards compatible with different legacy VPN implementations that might use crypto maps and so on. It uses the next generation key management protocol, IPv2, RFC 40, gosh, I can't remember, 4300 something. I can't remember the specific number. So that has a whole bunch of enhancements of the original IKE protocol. It does mutual authentication when we're establishing SAs as opposed to unidirectional or client or server-based authentication or client-based authentication. It supports peer-to-peer configurations on a per-peer basis, meaning that I can apply different service parameters, firewall mechanisms, firewall policies, VRF-related routing policies, QoS policies on a per-peer basis. Again, a lot of flexibility, all right? And I keep mentioning this, but this, and they mention it again in the book here, but this is really one of the biggest keys, right? The ability to encompass both remote access VPN solutions with site-to-site VPNs. Now, I'm not saying you can't do that on a router or a firewall, but they would be completely separate and disparate configurations, right? In this particular case, those configurations are merged together, and we provide those features together in the same configuration, okay? We can work with AAA databases, and that allows for things like multi-tenancy and so on, and this is Cisco's little take on it. Recommended for the future. So if I was to say this in a salesy way, I'd say FlexVPN. It's the future technology of choice for VPN solutions, right? And that's really what it is. So you will see, you may not be implementing it now, and it may not come in the near future, the near future, but eventually you will see people migrating to this technology because of its flexibility and being able to handle all different types of VPN scenarios. Okay? All right? One single FlexVPN deployment can accept connections of remote access or site-to-site at the same time. All right? We see that, we didn't talk about EasyVPN, but we see that in this case, EasyVPN is probably the least preferred method. We can see no spoke-to-spoke communication, no dynamic routing, etc. The dynamic routing is a big point, right? Now, if I compare this to DMVPN, which is really what we would do, right? I mean, that's really DMVPN is the predominant, VPN architecture that's in place today. Yeah, we can do dynamic routing and spoke-to-spoke communication on both of those. Obviously, there's a little asterisk here. We have to run phase 2 or better. But no remote access, no configuration push to the spokes. The spokes have to be statically configured. In FlexVPN, the configuration can be pushed out to the spokes. That means all the policies, the keying policy, the encryption policies, the SA policies, they can be pushed out. We don't have per-peer configuration in DMVPN. Whatever policy we apply to our DMVPN architecture has to be applied to every peer. All right? So we have group QoS, but we don't have per-peer QoS, right? And there's no AAA management in DMVPN. Quite frankly, it's not really required because there's no remote access support. So we don't really need that AAA integration in a DMVPN environment. I wouldn't necessarily say that is a fault of DMVPN. It's just not necessary. Okay? To implement FlexVPN on a router, we have several different, if you will, building blocks that have to be configured, and some of them are customized, some of them have to be configured, some of them we can use defaults, okay? Again, we don't get into the specifics of it in this class, but I'll give you an idea of what these building blocks are and maybe kind of summarize what each of these building blocks are. I'll start with the top one here, the IKE v2 proposal. Very similar to what we saw in IKE v1, right? It's going to define the protection mechanisms or the attributes that we're going to use for the negotiation of our security association, right? What kind of encryption am I going to use? What kind of hashing algorithm am I going to use? What kind of a lifetime am I specifying for the tunnel information and so on? All right? The proposals, we can have multiple proposals configured. They're actually configured by default, and then the peers will select a proposal based on whatever the best possible match is. Okay? The second building block is the policy itself. This is what is going to bind the proposal to the actual VPN peer. Okay? In IKE v2, that policy references the actual proposal. All right? Again, in the CCNP security, we actually configure this. so you get to see these different configurations. If I get a chance, I'll put together a lab and kind of show you all of these different building blocks in that lab exercise. Okay? The key ring, obviously used to define the keys. These are the pre-shared keys that allow us to authenticate the peers. The keys do not have to be symmetric in IKE v2. They can be asymmetric, meaning that I can use different authentication keys on each end of the IKE session. Then we have something called the IKE profile, and this is really what ties everything together, right? It is a repository of all of the non-negotiable parameters of the IKE SA. Proposals are negotiable. Policies are negotiable. Keys, well, they're not so negotiable, but they can be configured asymmetrically. There is no default IKE v2 profile. You actually have to configure one, and then you attach it to the IPSec profile in the next step, right? If we're using, for example, pre-shared key authentication, the profile references the key ring that we're using in that process, in that authentication process. But we are going to specify all of the unnegotiated parameters of the SA. All right? Then we have our IPSec transform set. That's going to specify all the acceptable combination of security protocols that are going to be used for phase 2 of the encryption process, right? The IPSec SAs. What kind of encryption am I using? What kind of hashing method am I using? What's my rekeying policy, etc. Okay? And then finally, the IPSec profile. All right? The IPSec profile is the configuration that allows us to summarize the FlexVPN settings into a single profile that gets applied to the interface. So this can reference the IPSec transform set, it can reference the IKE v2 profile, and this is what allows remote access VPN connectivity, site-to-site VPN connectivity, and so on. All right? There is a feature, and hopefully I'll be able to show you this at some point in the future. There is a feature called Smart Defaults. It's an IKE v2 feature that helps us minimize the amount of configuration that's required with FlexVPN. It basically just includes a whole bunch of default settings for all of these different configuration blocks, except the keyring, which is uniquely configured, and the IKE v2 profile, which is uniquely configured. All right? We can customize those smart defaults, by the way, if I decide that I want to apply those smart defaults but not have necessarily default values. So I have the ability to kind of customize that in the future. Okay? Wow. Only 3 hours and 40 minutes later, we're finished with this particular lab, or this particular discussion. We talked about GRE and classic GRE and private routing over public networks, how to add encryption or IPSec tunnels to that IPSec encryption to those GRE tunnels. We talked a lot about DMVPN, the different phases of DMVPN and how we progress through the different phases to provide us different features. Obviously, phase 2 being pretty much the preferred method, especially if I want that spoke-to-spoke communication. Phase 3 added, of course, the ability to do summarization and that initial caching of the routing information by sending the packet up to the hub initially and then using the NHRP redirects to redirect that traffic. And then we talked about FlexVPN and really high level, of course, and what the benefit of FlexVPN is and why we might consider using it. So that concludes that lesson. All right?
Thanks, Scott.